Okay. So, good morning, everyone. I'm very, very, very happy that you are all here. Welcome to Cuernavaca. It's really moving, and I'm sure it will be a fantastic conference. Thanks to each one of you for being here. And we'll have just first a very few words from our chairman in Cuernavaca, and then we'll move towards the lectures. Please. He's Salvador Pérez Esteva, chairman of this institute in Cuernavaca. Gracias, chairman.
Well, we're very happy of being here celebrating Pepe's birthday. Pardon me? 50 plus 20 or something like that. Yes, Pepe, you know his mathematical achievements, I'm not going to talk about that at all. But I want to express that Pepe has been a key person, a fundamental person in the creation and in the success of this branch here in Cuernavaca. So we are, all of us here working here are very grateful. He's a dear friend for everyone, in particular mine, and it was obvious that his celebration had to be here. And it's excellent. This looks like it's going to be a fantastic conference. We have a long tradition since we started. Maybe some of you were here back in '67 with that international year of dynamical systems and 96. I'm sorry, I'm sorry, 96. And since then, we have had many excellent conferences, and I'm sure this is not going to be the exception. And I wish you all the success in the world. So, well, and this is your home, and you're very welcome, and have a good conference. A ver cómo lo acomodo. Yeah, okay. Maybe on the bottom.
Is this going well? Good. Thank you very much. So, of course, I'm very grateful to the organizers. Thank them very much. I can't say how happy and honored to be here for Pepe's birthday. I'm going to talk about valuations, which is the same subject I talked about 10 years ago in Merida for the fest in honor of Pepe's 60th birthday. I'm sorry, we all know that you are more than 50. But I'm happy to report that there has been some progress since then, so it won't be the same talk as 10 years ago in Merida. Sorry, same notations, yes. Okay, so for those who were not there or who have forgotten, which is quite excusable, let me first remind you of some well-known facts about curves. So for me, think about formal branches. Formal branch is a complete one-dimensional Noetherian domain over K, which is an algebraically closed field. Okay. So, of course, you can think of a certain number of power series in one variable in some affine space. And I will always assume that, so a Noetherian domain, I assume it's a K algebra.
What's the intuitive meaning of one-dimensional?
Curve. So it's a curve because by Newton's theorem, we know that in this case, the ring R is a subring of the formal power series in one variable. And if you take a system of, say, generators of the maximal ideal of R, then this gives us series. And this is our parametrized curve in affine space of dimension n over the field K. Okay, so it's a curve, given parametrically or not. You can give you a ring. That means you take a certain subring of the power series ring with certain properties, or you can think of parametrization. Now, there is a problem of, so this, in a way, it's a resolution of singularities because this is a birational map. They are the same field of fractions. Which is K of t. So this is what one usually calls the resolution of singularities, a non-singular model of your curve. But I'll be talking about the problem of embedded resolution, which is quite a bit stronger. So embedded resolution is a birational map, again. Well, this is non-singular, again. So it's birational, so they have the same dimension, such that if I look at my curve, which I write x, given in here, if you can think of it as parametric, there is a representative of x, there is a lifting of the parametrization to Zn, which is non-singular. That means the image will be a curve in Zn, which maps birationally to x, and this is non-singular. Of course, in general, the curve, as I gave it here, is singular because the series can all be of order greater than 2.
What's the difference between x tilde
X tilde is the strict transform of my curve under this birational map. That means that I'm assuming that this map is X is contained in the open set above which the map, say pi here, is an isomorphism. So that means I can look at the part of X which is in U, I can lift it to Z, and then take the closure. That's the definition of the strict transform. And what I want is that the strict transform is non-singular. So this is called embedded resolution. It's much more useful than resolution proper. Now, in the case of plane curves, where we have this plane and the characteristic of K is 0, then this is a beautiful chapter of singularity theory, which is well known, that you can build, then the curve has numerical invariants, which are called the Puiseux exponents. I don't have time to go back, and I think most of you know about that. And from these Puiseux exponents, the Italian geometers described an embedded resolution of the curve by a succession of point blowing-ups. So you can blow up a point in the plane, you get a new non-singular surface through which your curve goes, and then you go on blowing up, and after finitely many steps, you get this situation. So this is a composition of point blowing-ups. Not really, because Puiseux exponents are only over algebraically closed field. Well, Newton invented Puiseux expansions over the reals. But for this to work, you have to have an algebraically closed field, because you have to extract roots successively. So usually over C. I mean, Italian geometry was mostly over C. Okay? Now, if the embedding dimension is greater than 2, or the characteristic of K is not 0, then this beautiful story breaks down. You cannot, in general, describe well, you can still blow up. I mean, you can still prove resolution, but it's a very messy process, and there is not a beautiful description like in the case of plane curves. And if the characteristic of K is 0, then it's basically a completely different process if you want to resolve singularities by blowing up points. There are papers about this. It is that it's possible, but it's not nice. It's messy. As soon as you are not dealing with, for example, so let me now come to the subject of my talk. If you look at this inclusion, in this ring you have evaluation, which is the t-adic order. You can restrict it to R. So you get integers, of course, and these integers form a semigroup, because when you multiply in R, the values add. So you get a numerical semigroup, gamma, in the semigroup of integers, and such a semigroup is always finitely generated. So you have another set, you have a finite set of integers, which is another set of numerical invariants. And in fact, if we are in characteristic 0, this set is in order preserving bijection with the set of characteristic piezo exponents. If you think of them as integers, then there is a formula due to Zariski, which relates the two, and it's an order preserving bijection. So in characteristic 0, you don't really need the semigroup, as I explained. But in positive characteristic, first of all, there is in general no piezo expansion at all. And second, even when there is one, which means you can identify certain exponents in the series, this bijection completely breaks down. And in fact, it's unknown. There are examples of a curve with 4 piezo exponents and 5 generators of the semigroup. And I don't think it's known whether there is any kind of manageable relation between the two in positive characteristics. However, what is true, and what I'm going to explain, is this guy, the semigroup, in any characteristic, contains all the information needed to resolve, to prove embedded resolution of curves. And in the second part of my talk, I will generalize. So what happens? What happens is that you can, on R, you can define a filtration, and I will use the notation I will use later. So phi now is an integer in this case, but later it will be an element of a group. I should add 0 because there's always this mess. I should always remove 0 because 0 has value infinity. So either you add the infinity, you take n union infinity. Infinity is the valuation of 0. Or you always have to remove 0 from R. And then you have to add the 0 in R again because otherwise it wouldn't be an ideal. Anyway, you have this filtration. Now, it's a very natural filtration because it tells you essentially what is the order of T of an element, in T of an element of R. So it is natural to look at the graded algebra associated to this filtration. And it turns out that this graded algebra is isomorphic. It's not difficult to prove at all to the algebra of the semigroup gamma. In fact, well, that's the way it is. Why? Basically because when you look at the order, if you take any non-zero quotient, you take elements of order t modulo elements of order greater than t. Well, that is just some element.
But gamma has one branch, right? Or not?
I'm talking about a branch, yes, yes. Each of those quotients, which is not zero, is a one-dimensional vector space over K. And this is, it's almost obvious. You look at a series in A t to the n modulo series in t to the n plus 1. So what you are left with is A. Anyway, so this is the characteristic of the semigroup algebra, that each one of its non-zero graded components is a one-dimensional vector space over K. Okay? Now, what is important here? What is important is that, so this is, again, I can write it as t to the gamma 0, t to the gamma g. And now the first step is that this is the algebra, a monomial curve. What is a monomial curve? It's a curve which is parameterized by monomials. The terminology is such that a monomial curve is defined by binomials, because such a monomial curve is a quotient. This one is a quotient of a polynomial algebra in G plus 1 variable modulo an idea generated by binomials. This is a very easy exercise using the fact that every non-zero homogeneous component is of dimension 1. So this is the place where we connect valuation theory with toric geometry, because this is a toric object, it's a toric curve, and this comes from the fact that this graded ring associated to the algebra has the property that every non-zero homogeneous component is a one-dimensional vector space. So this is where the bridge is made. And now the next thing is that it's a general principle of commutative algebra and even non-commutative algebra, that whenever you have a ring with a filtration, you have a specialization from the ring to the graded ring. Now you can look at this as an algebraist, graded ring, and try to prove that if it is Gorenstein, then the ring is Gorenstein, if it is this, and the ring is that. But the way I look at it is like this. There is a family of curves parameterized by the line, such that for every 0 point of the line, the fiber is isomorphic to my original curve. That means the ring R. And for 0, I get C to the gamma. There is a geometric specialization from the ring to, and this specialization has the property that all the fibers are isomorphic, except the special one. Now, this is a general fact. Now, the next important thing is that in this case, because we are dealing with evaluation, this family is in fact an equisingular family of curves in some sense, in the sense that the whole family here has an embedded resolution, a simultaneous embedded resolution by non-singular curves. And this is the point. So how do we look at that? We look at this in the following way. I have generators of this graded algebra. Let me call them xi I bar. They are elements, they are in bijection with the generators of the semigroup. So they are elements of these quotients. The non-zero quotients, the algebra is generated by the images of the t to the gamma I. The t to the gamma in this, they generate this as an algebra. So I take elements of R, which are some xi I in R, whose images in the quotient ring, each one of them has an image in such a quotient, generate this algebra. So there are exactly G plus 1 of them. Of course, I have some choice because I can add terms of higher order in T, in R, but they exist, okay? So this means that I have a map, a surjective map, from the power series ring in variables U0, UG to R, which maps Ui to psi I of T. What this is actually an embedding of my original curve X, which was embedded in some affine space, but now I embed it in some other affine space. And this is why the title of my talk is what it is. It says, what is the interest of embedding? So if you embed your curve, which was originally n may be equal to 2, no matter, you embed it in the space of dimension exactly the number of generators of the semigroup, then you get a very pleasant surprise, is that then X as embedded in here specializes to the monomial curve. Why? Because, well, I don't have time to give all the details, but in this space with the coordinates U0, UG, your curve here is given by equations like this. So if I give each variable the weight gamma I, this is very important. I have my variable. This is a power series ring, but the variables have weights. The weight of Ui is the value of it's I. And the equations for X as embedded in this, they can be written as follows, where the weight is strictly large. The weight, these two monomials have the same weight. They correspond to relations between the gamma I. I should have explained. When I write T to the gamma I, there are relations, okay? And the psi I, which are essentially the same, their initial forms are relations. This explains the lambda here. Because when I say that this algebra is isomorphic, this one is really generated by binomials like this, but the isomorphism comes into play. I don't want to explain, it's not very interesting. And instead of having 1 as a coefficient here, you have some non-zero coefficient. Okay, like this. Okay, so my curve, when I re-embed it in EJ plus 1 like this, I can write down its equations, and this tells me you can, it's a bit more delicate, but you can very well imagine that you put some deformation parameter here, and for V non-zero is going to give you the curve as parameterized, and for V equals 0, you will get the monomial curve, or the curve which is isomorphic to a monomial curve. Now, this is what I call an overweight deformation, because I add only terms of greater weight. And it turns out that these binomials, the toric variety generated by these binomials, which is essentially a toric curve, can be resolved by a toric map. What is a toric map? I don't want to take the time to explain, but Z is covered by affine charts, and in each chart, this map is monomial. So it is as simple as you want, and these monomials, if you look at their exponents, they form a matrix which is unimodal. So this is a birational toric map. So the theorem is that you have, it was proved with Pedro González Pérez many years ago, that if you have any toric variety like that, you can find an embedded resolution like this, which will, so any binomial variety like this, you can find an embedded resolution by toric map. Now, in this guy, I have my original affine space, and in this guy, I have my original curve. Now, the map can be chosen. This is so that the strict transform is non-singular, and the strict transform of X sitting in there is non-singular. So this is really, this guy is an embedded resolution as in the classical sense, birational, strict transform, non-singular. But the advantage of this method is that it's totally blind to the characteristic, because the resolution of singularities of toric varieties does not see the characteristic. So this tells you that the real object to look at for curves is the semigroup. Forget about anything looking like Puiseux, whatever, semigroup. It's the guy who contains the information for the resolution. Okay, and you must keep in mind that this is a very geometric fact, but this specialization is only equisingular once you have re-embedded your curve. It is your curve once re-embedded in AG plus 1, which will then nicely specialize. Otherwise, you cannot write the equations. Okay? And once you know a bit about toric geometry, it's very easy to see that a toric resolution of this guy, of this binomial part, will extend to the whole thing. Okay. So, well, I guess this was the first part. Yes.
Excuse me, in the case of characteristic zero and plane curve, this specialization has the same Puiseux expansion than...
Well, no, because what you get in terms of power series, what you get are series like this. And this series begins like this. The orders are, sorry. So my curve is embedded in AJ plus 1. Parametrically, it will be given like this. So the initial, all you can see is this gamma I. But it turns out, as I said, in order to understand the geometry, you can forget about those terms once you are embedded in EJ plus 1. So there is no, how to say, there is no nice topological interpretation, if that's your question, of this embedding into AG plus 1. But what you can say is that for plane curves, because this is true for any branch in any space, but if you look only at plane branches, then the semigroups are very special. The monomial curve is a complete intersection. The equations look like ui to the ni minus lambda I u0 to the something ui minus 1 to the something plus higher order. So even the binomial equations are special. And it turns out that these equations are ordered by the order of the ui. So you have, in fact, g plus 1 equations, or g equations in AG plus 1, because it's a curve. You have g equations. Now, if you forget the first k, if you forget, sorry, the last k, you get g minus k equations. And you can make eliminations, and this will give you a new plane curve. And what is this new plane curve? It is the plane curve whose Puiseux expansion is the old Puiseux expansion truncated just before the ith Puiseux exponent. And geometrically, this gives you a system of knots which approximates the final knot of the curve. So everything is not lost. In the case of plane curves, from this construction, you can recover all the nice by just eliminating and going back to the case. Okay. Now, the goal is not, it's already, I think, did I miss something about eraser? Oh, okay, thank you. So this suggested a program if we can do it for curve, and if it is blind to the characteristic, then why can't we do it for any singularity. Why not? So the idea is, maybe I should erase this too. Suppose I have, let us say, a domain, or an irreducible algebraic variety in some affine space. Sorry, I should do it like that. So can I find a re-embedding and a toric map, birational, such that, well, the same pictures go through? Toric map such that the strict transform of my original affine space is non-singular and the strict transform of X is non-singular. It works for curves, so why not? Well, it looks crazy, but it isn't, because after hearing this in Oberwolfach, Tevelef proved, I'm not going to write it because I'm going to be short of time, I think. Well, anyway, Tevelef I should write. Prove that anytime you have an embedded, in fact, it's in the projective case, so replace affine by projective space, doesn't make much difference. So suppose this is projective space. X is an irreducible projective variety. Anytime, so that's what Tevelef proved. Anytime I have a projective variety like this, which has an embedded resolution. So this is some birational modification of the projective space. This is the strict transform, it is smooth. So Tevelef proved every time you have this situation, you can re-embed the original projective space into a larger one and find a toric map so that this works. And sorry, it's still not smooth, yes.
So that's the resolution of
So that's the resolution of singularity. Every time, no. Every time you are given an embedded resolution, which does not exist in positive characteristic, you have this. So in characteristic 0, you have this. So that's very encouraging. Okay? So, but now, of course,
Zero, what is the geometric meaning of this?
in characteristic 0, well, I should have said that. What do I do for the plane curve case, for example? I re-embed my curve in some space where there are sufficiently many hyperplanes. Each generator of the semigroup is the intersection multiplicity with a hyperplane. Okay? Tevelef's proof, of course, it's much more fancy, but you re-embed such that in this space you have sufficiently many hyperplanes so that they sort of sweep through all the exceptional divisors of the given embedded resolution. So you get all the geometric information. Yeah, and of that there is a nice lemma which he proved with Keen, I think, which says that such a situation can always be realized torically, in a toric way. Okay, this is second year toric geometry, or maybe even third year toric geometry. But it's like that it works. So the basic idea geometrically is to have sufficient many hyperplanes to sweep through all the information you need, and you don't know. But of course, then you have to translate that into nice algebraic terms. Okay. So now valuations. This is so another thing is when we don't have embedded resolution, how to find this embedding. Now, of course, Zariski showed us the way many years ago, because evaluation on the function field of X is something which picks a point in every birational model. Okay, so Zariski's idea was first find birational models, given evaluation, first find birational models where the point picked by the evaluation is a non-singular point. Once you have that, then there are methods to spread it out. It didn't quite work out in Zariski's case, but I'm more optimistic in this case. But anyway, some years to go, I suppose. But for the moment, what I want to do is to show you that given certain types of valuations, which are essentially all the interesting ones, and with the assumption that your ring is complete, then you can find such an embedding. Okay. Now, let me. So so now R is no longer one-dimensional. It's a complete equicharacteristic local domain. Endowed with evaluation nu, where phi is a total. So it was Z for curves. Now it's a totally ordered abelian group. And I look only at my evaluation takes values in the positive part, just as we did for curves. And we had defined the dimension of phi tensor Q over Z, so-called rational rank. So rational rank has a very obvious algebraic interpretations, the maximum number of rationally independent elements in phi, and I hope that permits, I will give you a geometric interpretation. So I make some more assumptions on evaluation. One is that it's a rational variation. I don't want to explain. It means that, assuming you work over an algebraically closed field, it means that the point which is picked in every birational model is a rational point. It's a closed point. Because valuations pick points in every birational model, but these are scheme-theoretic points, which means they are irreducible subvarieties. So rational valuations are those which pick a point, a real, honest-to-God point. Okay? And this has the consequence that if I look at the graded ring associated with the variation, then each homogeneous, each non-zero homogeneous component is a one-dimensional vector space over K. It can be proved, and in fact I proved many years ago, that if you want to prove local uniformization in general, it's enough to prove local uniformization for those guys. Because local uniformization, if you think of a variation which picks some subvariety, and what you want to prove for local uniformization is that the X tilde is non-singular at the general point of this subvariety. But the general point contains many close points. So if you can prove that whenever you get a close point, it's non-singular there, it will be non-singular at all the points which are of higher dimension. So these are the only really interesting ones. It's not the usual method of people who do local uniformization, because people like valuations of rank 1, which means that the value group rank 1 means phi is a subgroup, an ordered subgroup of R. The rank tells you that there may be many elements in the group which are infinitely large with respect to others. Maybe I should take a minute. Rank 2 typical is the group where you take Z2 with with the Lex ordering. Okay? So if you take Lex ordering, all the points, so this is I, this is J. So you look at the first coordinate, and if it is greater than 0, then your element is greater than 0. So all the elements of these lines in the positive part of the group. The only elements where the whole line is not in the positive part are those guys, because if I equals 0, then you compare the second coordinate. Okay? Ij is less than I prime. J prime means that either I is less than I prime, or I equals I prime and J is less than J prime. Okay? So any element on this line is greater than any element on this line. And any element in this line is positive. So for example, this is not well ordered, because, I mean, the positive part is not well ordered, because you can see with your own eyes an infinite decreasing sequence of positive elements. Okay? So people don't like that, because people like well orderings. Okay? But I like them. I'm a bit of a contrary temperament. Anyway, so, but if you look only at rank 1, then these variations which I'm talking about are not sufficient. So anyway, let's go back. So my variations, I mean, the rational variation, they have this property. So this implies, and this is an easy exercise, second step, one should know that gamma, which is the semigroup of values, is not, in general, finitely generated. And this has nothing to do with the complexity of the singularity of R. It's just a fact of life. For example, you can take any sequence of rational elements, positive rational numbers, such that none of them is in the semigroup generated by the preceding ones. Okay? Can you imagine? Like you take SI's, integers, and you take NI SI plus 1 over, this is Zariski's example, by the way. A sequence of rational numbers, the SI's are integers which are greater than 2, NI are some natural numbers, and you take a sequence of rational numbers like this, then none of them can be in the semigroup generated by the previous one because the denominators increase, and you can always find a variation whose value semigroup is generated by those guys, even in the plane. Okay.
Gamma countable?
Excuse me?
Gamma.
Yes, always countable.
Huh?
Yes, yes, you're right. I should have said that. Always countable. Yeah, in fact, phi is embedded in Q to some power because my ring is Noetherian. This has nothing to do with algebraic geometry, by the way. I mean, it has only to do with the fact that R is Noetherian. Anyway, let's continue. So, if gamma may happen to be finitely generated, then essentially, it's not quite true as I said, but almost, and it doesn't really make matter. Then it's called an Abianca evaluation. And this is the case where the cruel dimension, so there is something that is known as Abianca's inequality in this case, in the case of rational evaluations. In the general case, you have to put in another invariant. But in the case of rational evaluation, you always have this inequality. This is a cruel dimension because, as I said, this may not be Noetherian. But anyway, it has a dimension. And if you think about it, it's unnatural, like many good things in evaluation theory, because I explained to you that R specializes to GRU R. So in general, when you specialize, the dimension increases. But here, no. Because the semi-continuity of dimension is proved under finiteness assumptions, which exactly are not realized here. Because granula, in this case, is not Noetherian, not finitely generated, if the semigroup is not finitely generated. But if the gamma is finitely generated, then it means the dimension of granula is equal to the dimension of R. And in this case, basically, the method for curves works. Of course, it's a little bit more technical, but what I did for curves in this case, it works perfectly well. You re-embed in a finite dimensional space, which correspond to generators of the semigroup, and then you prove that in this specialization, the toric resolution of the graded ring does indeed uniformize the valuation. This is basically what I talked about 10 years ago. Now, the progress since is that now I know how to treat the case where gamma is not finitely generated. And here it's
What about examples? You have an example.
Ah, yes, but I know later if you want, but not now. Yes, that's why I am. So let me explain very quickly what happens. The main thing is that, so let me say that gamma is, because gamma is well ordered. This is always well ordered. This is fundamental. Why is it well ordered? It's because the ring is Noetherian. If you had a decreasing sequence of elements of gamma, you would have an increasing sequence of ideals, of the valuation ideas, P phi. So, no way. Gamma is always well ordered. This is absolutely fundamental. People who do local uniformization in the classical way, they deal with value groups, and therefore value semigroups, positive elements. Positive elements are not, as I explained, well ordered. So this is like fighting with one hand behind your back, or maybe two. So gamma is well ordered. This is absolutely fundamental. So I have a well-ordered set of indices. Now, the way this thing works, so I'm going to, of course, talk about the case where gamma is not finitely generated. The problem is to find good approximations of gamma by finitely generated semigroup, so that you can make the construction which works in the Abianca case and hope that it will have the same effect. Well, in practice, it's a bit more complicated, but let me explain. First of all, one can find a sequence of finite set in I. So the BAs are finite, and they are what I call initial. Initial is something which is easy to understand in the case of rank 1, because in the case of rank 1, everything is on a line. So initial just means that it's the set of gamma than something. This is obviously in the rank 1 case, this is always a finite set. And that's it. So they are initial in the most naive sense. But if you have rank greater than 1, you have to cook up a definition which works, which I did. But I won't give it to you because I don't have the time. So there are finite initial sets whose limits, of course, is I. Now to each of these. Now the second thing is to build a generalized power series ring, which I denote like this. So this is again, so I put a hat. This is the set of all series with DE in K and U to the E, any monomial. Okay? And because gamma is finitely generated, it turns out that you can multiply two such series And this is indeed an algebra. It's a very nice generalization of a power series algebra. In fact, if I is finite, of course, it is a power series algebra. So it is, it's in everything. You can substitute series inside series. It has all the properties of power series ring, except, of course, notarianity. Okay? Now the next step is to build the equivalent of what we did for curve, to build a formal embedding of our space corresponding to R in some infinite dimensional space. This is done by what I call the valuative Cohen theorem, which is constructing a map. So this means finding elements in R such that the map which maps UI. So these are representative of generators psi I bar in the graded ring. The graded ring is no longer finitely generated, but it still has the generators of the semigroup as a set of generators. So, and here this is absolutely non-trivial because you have to choose the representatives. You cannot choose any representatives because what you want is that as the value of this representative grows, the m-adic value in R increases. And because, except in rank 1, this is not given, this is not true in general. You can have increasing values and constant m-adic order. If you look at the example I gave earlier, if you look at x plus y to the I, the m-adic value, the new adic value increases with I, but the m-adic order is constantly 1. So you have to choose your, this is not quite obvious, such that if you look at the corresponding associated graded rings, which are in this case the polynomial ring, and in the graded ring, then you maps to psi I bar, which is the image of psi I in the graded ring. So this I call the valuative Cohen theorem because it is the extension of the usual Cohen theorem, which tells you that if you have a complete equicharacteristic Noetherian local ring, you look at the associated graded ring, the tangent cone, if you like, you take a set of generators, you lift it in any way you like, and it gives you a map from the power series ring to your ring, which is surjective. Okay? So I always loved Cohen theorem because it gives geometric meaning to any complete equicharacteristic Noetherian local ring. So because I love it, I generalize it to this situation. And then, using this, so this gives me morally my re-embedding, but it re-embeds my space in an infinite dimensional space. That's not so cool because you cannot hope to, and this guy is not finitely generated, it's still toric in the sense that the kernel of this is generated by binomials, of course, infinitely many binomials now. So it's still a toric variety in an extended sense. But of course, it has no resolution of singularities because you have infinitely many singular equations, so forget it. But so what did I do? To each of my finite set BA, because of this map, I can associate an ideal KBA in R and evaluation nu BA on the quotient, which is which has finitely generated semigroup gamma BA in gamma, and the valuations nu BA approximate nu in the sense that any x which is not 0, there exists A so that x does not belong to, there exists A0 to KBA for A greater than A0, and the value of X is computed in the quotient. Okay, so it approximates nu. The semigroups are finitely generated. Of course, the union is gamma. And then there remains to prove, or to tell you one can prove, it's not quite finished yet. So let's call this work in progress. That these valuations which I mentioned, this valuation nu B, I forgot. These are Bianchi valuations. The dimension of this, they're all of the same dimension, which is R, which is the rational rank of nu. Now I told you that for Bianchi evaluations, one could prove local uniformization by toric re-embedding, which, by the way, he's saying, Tada and I, we call that a torification, which is a mixture of torific and toric. We call this a torific embedding. So for Bianchi evaluations, we have the proof of torific embeddings. So for sufficiently large A, one, it's not quite finished, as I said, proves that a torific embedding of this Bianchi evaluation with certain extra data corresponding to the fact that still it comes from R will uniformize the valuation nu. So this is supposed to end the proof of local uniformization for all valuations, in fact, in Noetherian complete local equicharacteristic algebras with an algebraically closed residue field, which is very important. And this is also the end of my talk.
So is there any question?
This always has, this has the assumption there's an embedded resolution.
No, no, of course not. The idea is to prove everything without assuming the existence of an embedded resolution. The idea is if you start with a singularity and you want to find some torific embedding, if you already have an embedded resolution, then you do like TVLF. You start from the embedded resolution, you look at many linear systems and this and that. But here we have nothing. We have the ring, it's a equicharacteristic. So how can we hope to find some torific embedding? Well, the idea is if you look only at the local uniformization part, which is a kind of very local part, then you have the semigroup. And you work with the semigroup, which is what I did. Okay? Now, suppose you can prove local uniformization for any valuation. Then what you do is you do like Zariski. You say, if I want to find a torific embedding, I have to glue up several. It's enough to look at finitely many valuations, that the compactness of the Riemann-Zariski manifold, okay, which is a very fundamental fact in all this. So by compactness, you only have to prove that you can find a torific embedding which will uniformize finitely many valuations, well chosen, of course. And I guess, I hope, I claim that it's much easier to glue torific embeddings than it is to glue local uniformizations like Zariski did. Because what Zariski did, you always have to worry about all the problems of birational maps doing this and doing that. But here you only have embeddings to glue.
Can I ask one more question?
Yes.
So, you're working under the idea that in positive characteristic, the resolution is still possible.
Yes.
You're working under that.
The assumption that it is true.
Huh?
The assumption that it is true.
Yeah, right.
Yes, yes.
But I was going to suggest or ask if you're finding extra structure without assuming a resolution. You're
Yes.
finding extra structure. You might find some obstructions to resolution from this extra structure.
Yes, but so far, no. You know, the idea is that always the semigroup, whether finitely generated or not, it contains the information you need to prove embedded local uniformization.
Thank you.
Okay. Any other question?
It's the first time I see this on all series with valuations.
Oh,
The usual power series have a nice subgroup starting with X and then Is there any analogous to this subgroup?
What do you mean? You mean the
All the series.
you mean, yeah, of course, given, in fact, if I choose B large enough, inside this I have the, this is a usual power series ring. Is that your question?
There's some group,
What group?
X plus higher order times.
Oh, inside this? Yes. Anything that exists for usual power series, you can do. Even you have even Euler's formula. If you look at all monomials, then it's a transfinite product. Anything you want.
Any
Except
other,
what comes from noetherianity.
other question? Okay. Maybe Daniel?
The process of gluing the local optimizations, are you planning or you expecting to use also Turing methods?
Oh, yes, of course. Yes, of course. The idea is, that's a good question. The idea is, ultimately, it should be a matter of refining fans. You do all this by refining fans. So here, from the semigroup, essentially from the binomials, the binomials give you hyperplanes in the dual space, in the space of fans. And what you have to do essentially is to find fans which are compatible with those hyperplanes and which are also compatible in some sense with the rest of the power series expansion. Okay? So the idea is that if you work very carefully, you can prove the existence of fans which refine finitely many fans with such and such properties. My friend Hussein Murtada has another approach. I say this, but you must, very, very nice, but you must ask him. I don't have the time to explain.
Just in the line that Dennis asked, you think, you hope this can lead to proving resolution of the singularities in general, or finding the obstructions for doing so?
Well, of course. I mean,
You're pointing in that direction.
Yeah, of course.
Yeah.
Of course. Yeah. I never thought I would try to do something in resolution of singularities beyond what I learned from Tanaka. But when I found this fact about curves, which I explained in the beginning, it completely changed my views. Now I think it is true. And I think also that one of the big differences of this approach with the classical approach, even if it has been refined and improved a lot, is that you don't look for an invariant to decrease. Because any invariant which has come to the conscience of the practitioners of resolution is essentially order or multiplicity and something like that. And the order and multiplicities have very bad properties. One of the very bad properties is that if you make a translation, then, and you have to when you make blowing ups, I mean in the classical sense, if you want to look, for example, at the center of valuation, with respect to the coordinates given by the blowing up, you have to make a translation. Now, when you make a translation, you find things like C plus A. And when you are in characteristic P, you find things like that. And then what you want is the linear term in, is that it? Yeah. The linear term disappears in characteristic P. Okay? A to the P. So, no, it's not quite that. Sorry, I'm a bit tired at the end. But anyway, translation is an enemy in positive characteristic. In toric geometry, it is a friend. Because whenever you make a toric modification, everything moves from the boundary of the toric variety to the torus. Then everything becomes complete intersections and life is beautiful. Of course, you have to work to prove that life is beautiful, but so it makes a big difference. For multiplicity, order, and all that, translations are enemies. for us, friend.
Okay, is there any other question? If not, maybe I can ask also some question. Philosophically, a question about the possible resolution of singularities. You mentioned, Ionaka proves that in the case of characteristic zero, resolution for algebraic context is the same as resolution in the complete. So it's the same resolution for polynomials. What do you think in characteristic P?
Well,
do you think it will be a difference or?
No. It's a very interesting question. In order to you have to decomplete. That's what you mean. You use completion in order to be able to make computations. And this is what I do here.
Yeah.
The relative Cohen theorem, basically completion. But there's a very simple statement which allows you to decomplete. And it is the fact that if you take now, R is no longer complete, but I assume that it is excellent. And apart from that, all the rest, equicharacteristic and so on. Then, and you have evaluation nu on R, which is again a rational evaluation. It has the same meaning. Then you want to understand what happens when you go from R to the completion. Okay? Suppose you can torify here. Then the conjecture is that there exists an extension nu hat on R hat modulo some an ideal whose intersection with R is 0, which has the same group. It's a very simple question. It's very surprising that nobody asked it before. Can you always extend the evaluation to some quotient of the completion with the same value group?
Okay.
It is true in two cases. Rank 1, this is basically one of the things Spivakowski proved, and I proved it for Abianca evaluations.
Okay.
Other than that, we are trying to prove it with Mark Spivakowski and two other guys that it is true in general, but it's tricky.
Okay, thank you very much. So if there is no more question, let's thank Bernard for this very interesting talk.
Thank you.
And then we will start at 11:10.
So before you go, please let me give you some information. So in the hotel, the breakfast starts at 7, and there will be some prepaid taxis at 8, 8:15, and 8:30.
For what? For what?
Since there are few of them, we will have to share. For the return to the hotel, there are some other taxis that will be available, but they are fewer than from the hotel. At the corner, there is a palapa that people is selling some books, and this cup is free, but it's also the only one that you are going to get. So please save it, keep it, because the university is dealing with some ecological programs, and is requiring us to avoid every disposal. So enjoy your stay in Cuernavaca.
Another advice, another information relevant. The trash, as Carlos said, the institute is part of a program that takes care of the trash and residues. We have several trash bins painted in different colors. One is for organic, the other is for plastic, the other is for paper, and the only important is the gray one, is the general trash. Please follow instructions in the trash bins. And another thing, in the bathroom, the only thing that goes through the toilet, to the WC, is paper. The paper that is rolled in hygienic paper is next on your right or on your left. All the feminine hygienic products, you have to dispose in some special bins that is only one in each bathroom. You have to find it. It's white, I believe, and that's it. Thank you very much.
One more thing. So tomorrow there will be some trip to Cortes Palace, and after that there will be some testing of mezcal. So if you don't know it already and you haven't paid, you have to pay it with the registration. It's 200 pesos, and there will be some guided to the Diego Rivera's painting. So it will be a nice trip. So enjoy.
Very nice concert after the...
Muchas gracias.
¿Dónde dejamos para estar?
Lo dejamos. Sí.
La verdad es que yo lamento no poder quedar
Hola, ¿qué tal? Sí, llegué tarde.
You were late.
Yeah, I was.
And you still ask a question. Is that allowed?
I love Power Series, so.
Okay, fair. Okay,
Every
you're
time
excused.
sorry for that.
No, I tell my graduate students, you come late. There's certain questions you're not allowed to ask because you're late. But you don't even know what they are.
But it wasn't very stupid because. Well, you say you can pick on Citas.
No, I'm
Series.
joking.
How are you?
Compared to what happens in Colombia,
Was that
We're
hard
all
to
getting old, right?
there has been some progress. People
Yeah.
try to prove the monotony conjecture vision.
Yeah, we are very happy to have you here.
Understood. If you want to work on that,
Welcome. Hola,
Hola,
soy Carlos.
Carlos.
Sí, en algún momento fui estudiante en Stony Brook. Sorry, hi. Michailovich.
Ah,
Pero ahora yo necesito hablar contigo porque
Sí.
tú vas a hacer una exposición
Sí.
que necesitamos quedar de acuerdo en dónde quieres hacerla.
necesito una mesa y nada más. Yo ya, no,
Aquí
nada.
mismo.
Sí, o ahí.
Otra opción es en esa parte donde va a ser la comida.
Porque es durante la comida.
Sí, y
Yo
ahí-
necesito una mesa y mostrarlo, no, nada complicado. Son cosas que las tiro ahí, son duras.
Bueno, pero sí.
No, durante
nos dices un lugar.
No, va a ser durante la comida. Por eso, mejor día, donde estemos comiendo y la pongo ahí, la gente puede comer, mirar, porque, ¿no?
Bien, entonces
Sí,
les pido
sí,
que
sí.
lo hagan ahí.
Sí, totalmente.
Perdón por la
Lo que
molestia y
sea-
por
No, por
interrumpir.
favor. Lo que sea más fácil.
Ya.
Ustedes deciden bien.
Bienvenida, creo que es la primera vez que vienes a Cuernavaca, ¿verdad?
A Cuernavaca sí.
Qué agradable.
Sí,
Fantástico.
una pena que sea tan corto, pero bueno.
Pero
mejor
das
corto
una
que
plática
nada.
mañana, ¿no?
Sí, no sé, una platiquita.
Yo creo que al ratito habría que anunciar lo de mañana, lo de tus superficies, no sé bien de qué se trata.
Quedamos en que va a ser en la terraza
Durante
mientras
la
gente está
comida.
comida.
Sí, eso está perfecto.
Voy a mostrar unas cosas también, ¿antes de la charla o después?
No,
No
eso
importa.
es antes de la charla, no, después. Sí,
Gracias por dar la charla. Yo también me siento un poco, no sé, está bien que de la charla, Pepe, yo no
Está
quiero
perfecto.
imponer,
Uy, no.
porque no es de este tema.
Aquí estás yo.
Ya sé, pero no es de este tema y me siento un poco, no quiero imponer.
Pues qué bueno que descansemos un poco. que está todo bien.
No, bienvenida,
No,
muy bienvenida.
Entonces,
es
primero,
un honor para
primero
nosotros.
es tu charla a las 11:10. Y luego yo digo que a la hora de la comida, allá mismo, allá arriba, ¿o dónde?
Incluso algunas de las cosas que voy a mostrar las voy a usar durante la charla porque muestro como utopías y cosas.
Ya, no,
Entonces,
Puedo hacer una preview. Porque Birthday Boy puede elegir alguna que puedo
Ok.
dejar si le interesa.
ok, muy bien. Entonces, a lo mejor conviene, no sé qué pienses, anunciar lo de ella justo al terminar su charla.
Sí.
ay, qué bonito.
Esto es una Steiner, tengo
bonito.
alguna más grande, Steiner Surface.
Ok, perfecto.
Y esto es, bueno, está un poco cortada, pero la Boy Surface,
Ok, muy bien.
bueno, ya explico mañana si mañana tengo tiempo.
¿Por qué no al terminar su charla se explica que después, que en la comida, Moira nos va
Sí,
a
o lo
estar
explico yo
interesados
también.
Bueno.
Le puedo decir durante la charla, como quieran, como sea más fácil.
como sea.
I'm easy going. La manera que sea más fácil, yo estoy muy agradecida que me inviten, todo lo que han hecho no puedo.
¿Eso lo has hecho tú?
Sí.
Qué impresionante.
No, esto no es nada.
Impresionante. ¿Qué hice?
No, yo lo puse, yo lo pego.
No todos tenemos privilegios.
Yo vengo con el mío porque tengo la espalda mal.
¿Cómo estás?
Necesito apoyarme.
Mañana te traigo un cojín si quieres.
Este es un inflable, lo traigo para el avión, para todos.
Yo no tengo, pero si quieres te puedo traer uno.
Pero Denis, no, porque él no, es distinto problema.
Mucho gusto y gracias.
La espalda se me curva más.
Hola Gregor, ¿cómo estás? ¿Todo bien? Hola señores, ¿cómo están? ¿Cómo les va? Ahí va. Me regañaron por andar llegando tarde y luego hacer una pregunta. No, Sullivan. No, no me vas a molestar. Hola, Melelao. ¿Cómo estás?
¿Cómo estás?
Qué gusto verte.
El gusto es mío.
Bienvenido.
¿Qué tal?
Hola Michelle, buenos días. Perdón por llegar tarde, pero se me reventó el boiler. Entonces había un charquero.
Problemas.
¿Eh? Sí, y por eso no llegué más temprano. Pero
bueno que estás aquí.
bienvenido, ¿todo bien?
Todo bien, todo disfrutando del calor, de la gente.
No, este calor no se puede disfrutar, es un infierno pequeñito. Es demasiado terrible.
¿Verdad?
No, pero pues hay lo que hay.
Sí.
Bienvenidos.
Gracias.
Hola.
Anda, qué gustazo.
¿Cómo estás,
Qué
Javier?
maravilla.
Laura, ¿cómo estás?
Qué gusto.
Y qué bonitos resultados. Los de Guadalupe, impresionante. Impresionante. El mundo raro es más difícil que complejo. Y ella lo logró.
¿Cómo vamos, Nacho? Viste, a Bianca sigue sonando, ¿eh? A Bianca.
Ya llenó la vuelta. Pues Alejandro está en Zurich.
Y
terminó su doctorado
¿Y Laurita sigue en Portugal? ¿Y en Porto?
Va.
Muy bien.
Creo que falta entonces mañana, es mañana lo del martes, ¿no? Pues llegué tarde porque se me reventó el boiler.
¿Qué?
Se reventó mi boiler. Entonces me levanté y había todo un charquero.
Pues si quieres ahorita vas a hacerlo, ¿lo vas a usar tú otra vez?
No, es para Inés.
Sí.
Él es el
Y
chef de la mañana.
¿Sabes qué? Si puedes checar con nuestros cuates que estén seguros de tener baterías de repuesto. Porque si de pronto se termina, no queremos. Es un desastre por eso. Entonces que al menos estén aquí y no tengan ese movimiento que ir a buscarlas y la chingada.
Ahorita va a hablar Daniel.
Sí. Bueno, Daniel,
¿Qué onda?
que se vea ese entusiasmo. No me vais a decepcionar.
No, si no me hago en los pantalones, que no con... A ver.
No es para calor, va a ser refrescante.
Esa cosa, déjame, me lo aprieto un poco.
Pues él ya toca jalar a la gente, pero lo que no veo es al chairman,
¿Quién es el chairman?
Nacho Luengo.
Ah, debe estar en el baño, no, no es cierto.
Esqueci todos os meus adaptadores em casa. Você tem algum adaptador para mim?
Tengo algún desadaptado.
Hola, hola. Hola, hola. Bueno, no funciona. Más bien. Hola, bueno. Sí, probando. ¿Se oye o no?
Ah, here is this.
Hola, probando. 1, 2, 3. Bueno. ¿Sí?
Nacho.
Okay, let's do this.
No tenemos campana. No, es que aplaudimos antes porque no sabemos cómo hacer la conferencia.
Ok.
Ya estoy suficientemente...
Muy buena.
Órale pues.
Para cada parte.
Hice lo que pudo. Órale pues. Ahí va. A ver qué tal. Ojalá te guste.
Okay, let's start again. It's time. So the next speaker is Daniel Duarte from Morelia. The title is here, so what you want? Okay.
Okay, so...
Thank you.
Well, firstly, thanks a lot to the organizers for inviting me to talk in this conference. It is a great honor, of course. I met Pepe about... no, sorry, are you hearing me? Hola, bueno, sí. ¿No? Aubin, ¿me oyes? No me oyes, ok. Sí, aquí está. Ok, hola. Ahora mejor. ¿Está mejor? ¿Escuchan? Yeah, it's clear now. Can you hear me? Okay. So I'm saying, okay, let me start again. So thanks to the organizers for the invitation to give a talk here. It's really an honor. And well, I met Pepe about 16 years ago, more or less. He offered a course on the topology of singularities. I was a master student here, and he offered this course, and difficult course. Okay, he nearly flunked me, but with the help with some friends, I managed to finish the course. And ever since, Pepe has been very supportive through advices, recommendation letters whenever I need them, financial support, and so on. So for all that, Pepe, thank you very much, and congratulations on your anniversary. Okay. So let me start with this talk, which is, you can see the title here, it's a little long. Okay, and this is a joint work with Wagner Badilla and Abel Castorena from Centro de Ciencias Matemáticas, okay, in Morelia. So the talk will be about the non-existence of negative weight derivations on some algebras. Okay, I will explain all of this. Okay, but first I would like to motivate to give the background of the problem. Okay, and it all starts with the classical problem of the classification of isolated hypersurface singularities. Okay, singularities. Okay, now, so throughout this talk, B0 will denote an isolated hypersurface singularity, defined by some holomorphic functions. Okay, x1 to xs. Okay. Now, associated to this function, or to this hypersurface, we have the classical Tijurina algebra, okay, which is the quotient of this ring, okay, modulo the f itself and all partial derivatives, okay, the Jacobian of f, okay. This is known as the Tijurina algebra, and with these ingredients, there is a classical, well-known theorem due to Mather and Zhao from 1982, which says that this algebra is a complete invariant of isolated hypersurface singularities and their biolomorphism. Okay, so B0 is biolomorphic to other hypersurface if and only if the corresponding Tijurina algebras are isomorphic as C algebras. Okay, this is classical, well-known theorem in singularity theory. Okay, now as a consequence, we have an injective map from the set of isolated hypersurface singularities, okay, to the set of commutative Artinian local algebras. Okay, to different hypersurface we associate different such algebras. Okay, and now it comes what Stephen Zhao calls the recognition problem. Okay, so among all these algebras, which ones come from this map, from an isolated hypersurface singularity? Okay, this is what Stephen calls the recognition problem, and in order to study this problem, he introduces or he studies the algebra of derivations of the Tijurina algebra. Okay, so let me denote it like this: the derivations over C of this Tijurina algebra. Okay, and using this module of derivations, he gives a necessary condition for this problem. Okay, so now we have another well-known classic theorem due to Zhao from 1991, which states that LB, okay, the one LB coming from an isolated hypersurface singularity, is a solvable Lie algebra. Okay, let me change the shock. Okay, this is a necessary condition for these algebras to come from an isolated hypersurface singularity. Okay.
Clarify what JFF is.
J of S, sorry, this is the Jacobian of f, just partial derivatives of f with respect to these s variables.
Is it the Jacobian or is it all partial derivative?
Okay, so this means partial with respect to x1 of f, and also and so on until partial with respect to xs of f.
All partial.
Yes, all partial derivatives. Yeah. Okay. And now, so after this theorem, this object became an important object of study. Okay, so there are many people that have studied this algebra. Okay, now among all these many aspects that have been studied, I want to emphasize the case of weighted homogeneous polynomials. Okay, so let f. Now I'm going to focus on the case where f is a weighted homogeneous polynomial. Okay? In this case, we take the Tijurina algebra as the quotient of the polynomial ring, okay? Again, by f and all derivatives of f.
Why did you label this
yeah, well, I don't know. I think this is the usual notation. Since f, this one is defined by this one, so maybe up to a unit it makes no difference. I don't know. I just follow the usual notation. V is V is the isolated hypersurface singularity. B of F, or F equals 0.
F defines B.
Yes, yes. So I'm sorry. This is like the usual usual notation. Okay. Well, anyway, now it's clear. I hope. Exactly. Exactly. One of the reasons. Okay. Okay. So now let me go back to this discussion. So I'm starting with a weighted homogeneous polynomial. F is homogeneous, then all partial derivatives are L, and so we have a graded algebra. Okay. So this we can give a graduation for this one. Okay. And then it is known that the algebra of derivations is also graded. Okay. In this case, L of B, sorry. L of B is also graded. Okay. I's, but now i's goes from minus infinity to infinity. Okay. Where each Li, I'm going to write it here, Li is the set of derivations. Okay. Sending homogeneous, yes, AI, Lj, sorry, this is J, I think. So J is the set of derivations sending homogeneous elements of degree I to homogeneous elements of degree I plus J for all I. Okay? So for example, in the polynomial ring, okay, you take a partial derivative with respect to some variable, then that derivative takes homogeneous polynomials of degree I to homogeneous polynomials of degree I minus 1. Okay, so this derivative is a minus 1 derivation. Okay, just an example. And so, okay, in this context, there is a conjecture by Zhao from 1996 stating that in this context, with all this notation, Lj is 0 for all j less than 0. In other words, on the Tijurina algebra coming from an isolated hypersurface singularity, there are no negative weight derivations. Okay? Say it again.
So if you just take f equal to xn equals 0.
But that's not a singularity. This x equals 0 is...
Just because
yes, I know. It sounds like a counterexample, but it has to be singular. Okay? Okay? Okay, so this is another important question from the 90s. And this question, a lot of people have worked on this. Okay, there are like lots of results. I'm not sure if it's already solved, but there's definitely real progress on this conjecture. Okay, so all of this is like the background. Okay, the historical motivation. Okay, all of these are classical results from the 80s and the 90s. And now I'm going to discuss, I want to introduce a higher version of all these objects and questions. Okay, so this the higher order version that I'm going to introduce, okay, that I'm going to mention, it was actually introduced by Stephen Zhao and some collaborators that I will mention in a moment. Okay, so the second part, let me talk of higher order versions. Okay, higher order versions of these objects and questions. Now, before giving, so these versions, they use or they're based on a higher order Jacobian matrix, okay, that involves higher order derivatives, okay. But before giving the definition, let me briefly mention that over the last 20 years or so, many higher order versions have been studied. Okay, they involve the Jacobian times powers of some ideal, Hessian matrices, or in general higher order derivatives. Okay, And all of this appears in the work of many people like Gruel, Lossen, Schustin, Dimka, Sticlaru, Pham, Jau, so, many people, okay? So this one is probably the most recent higher order version, okay? Now, in order to describe these new objects, I need to first define the higher order Jacobian matrix. Okay? Again? Is it what?
It's still open.
I really don't know. I really don't know. There is a yes. I don't know. I don't know. You know, because there are many papers on the subject, so I'm not sure if one of them already solved the conjecture. I don't think so, actually. I don't think so. Yeah. Okay. So now let me, before giving the definition, the object that Zhao and collaborators introduced, I need to define the following matrix. So consider, as before, so I'm going to take a polynomial, but it could be also a power series ring. Okay, so take a polynomial there, and I'm going to define as, or denote as, Jacobian n of f, okay, the following matrix. 1 over alpha minus beta factorial, okay, partial alpha minus beta of f with respect to these variables, okay. Here I'm using multi-index notation, okay. So this one goes, alpha and beta are vectors, okay, so beta in n to the s of module, let's recall that n minus 1, okay, this is the sum of the entries, alpha as well, and this was it goes from 1 to n, okay? So it is a matrix, huge matrix, involving partial derivatives of different orders, okay? Let me show you an example, and then you will see how it looks like, okay? So, for example, x3 minus y2, okay? So in this case, so for n equal 1, well, first property, for n equal 1, this is the usual partial derivatives, okay? So for n equal 2, it looks as follows, okay? It has partial derivatives, okay, first partial derivatives, and then second order partial derivatives divided by some factorials, okay? So here we have 3x, 0, and minus 1, okay? So the first row is always that. First order derivatives, second order derivatives, until nth order derivatives, okay? And then, using this first row, we construct the rest of the matrix by shifting it, okay, shifting the row and adding zeros. So here we have 0, 0, 3x squared minus 2y, 0, 0, 0, 0, 3x squared minus 2y. Okay?
So do you require that each entry of alpha is greater than beta?
Yes, yes, yes. Yeah, I don't want to go into all details, but if this doesn't make sense, just put a 0 there. Yeah. Okay? Okay, so and in general, this is what happens. Okay, for 3, Jack 3, we have first, second, and third order derivatives, bunch of zeros with first and second derivatives, bunch of zeros, and first order derivatives. Okay, this is the shape of the matrix. Okay, so at some point, Hussein, okay, now I'm gonna, let me name them. So at some point, Navid, Hussein, Woruima, okay, Stephen STS Zhao, and Huaixing Suom, okay, in 2022. They become interested in studying this matrix and to use it to propose new invariants of hypersurface singularities. Okay. So first, before going in direction. Let me just say that I originally introduced this matrix because I needed to do explicit computations with higher Nash blowups. Okay, this matrix was later rediscovered and further developed by several authors, and ever since we have seen some variety of applications. Okay, in the study of Nash blowups, in the study of homological properties of the module of principal parts, in the study of arc schemes, motivic integration, the study of invariants of rings in positive characteristic, and so on. Okay, so now let me discuss an application in this context. Okay, so they studied, or they proposed to study the following ideal. Okay, with the previous notation. Consider the ideal generated by maximal minors of this higher order Jacobian matrix. Okay, and then they defined n of B. Okay, B referring to the hypersurface defined by F as, again, this convergent series ring modulo F, and now we add this idea, this idea. Okay, and we can call this a Tijurina algebra of order n, for example. They name it differently, but let me use that name, Tijurina algebra of order n. And then they propose a series of conjectures regarding this algebra. Okay, so again, all of them propose the following conjectures. Okay. Okay. So first one, this is a biolomorphic invariant. Okay. So so as before, B0 biomorphic to 0 implies that these algebras are isomorphic as well. Okay, not W. Okay, this is the first conjecture. Then, second conjecture. There are two parts to this question. Yes. There is an isomorphism of the ambient space, and then it restricts to the hypersurfaces. Yeah. Okay. Now, first part. If F is weighted homogeneous, then the ideal of maxima minors is also weighted homogeneous. Is also weighted homogeneous. Okay? So once you know this algebra is graded. So it makes sense to talk about a graduation of the algebra of derivations. Okay? And so the second part of this question is, so in this case, once you know this is true, this one, Ln of B, is which is the derivations of tau nv. This one, inspired by Zhao's conjecture, has no negative derivations. Okay. Okay. So it is graded. It makes sense to ask whether there are negative components. Okay. So they say that there are no such components. And the third one is about, I won't give too much details here, but it's some conjecture that gives bounds for the dimension as a vector space of Lnv in some cases. Okay, so I will these two, but there is a conjecture. Okay, now all of them, as to motivate these conjectures, they Hussain, Ma, Zhao, and Suo, they focus on the case n equal to s equal to. Okay, just second order Theorin algebra, and two variables. Okay, so like plane curves. Okay. Yes. Yes, because the support of this one is the singular locus, and we are in the isolated hypersurface singularity. Yes.
Do you reach the end, the dimension increases or decreases?
Increases. Yeah, but this is actually the content of this conjecture. They say that for the set of derivations, not for tau n, the derivations on tau n, and I think they work just for weighted homogeneous polynomial, and they talk about some sort of universal bound in terms of some polynomials, something like that. Okay, so they study this the number. Okay, and okay, so I was saying that in this case, for these questions they studied the case of n equal 2. Okay, the first case after the known one. Okay, and two variables. Okay, and they ask the three questions affirmatively, of course. Just bound. Yeah. They give explicit bounds. They give some formula in terms of some specific polynomial. I can tell you the details later, but yeah, that's the idea of this. To bound. I don't have the exact statement. I can check it later and we'll talk about it. Yeah. Okay. And so, okay, let me just. Okay, I'm about to finish. Okay. I need the matrix. Sorry. Okay, so now the first question, theorem. Okay, this was so this is 2022. Now by October last year, there was a paper on the archive by Tuong, not the okay, not the one we know, our friend Tiang, Tuong Le, and Takeshi Koyasuda. This was okay. Then first conjecture is true. First conjecture is true. Okay, so they studied this question, okay, in full generality, any variables, any n, and they actually removed the isolated hypersurface singularity condition, okay? And it's a very elegant, very nice proof of just 7 pages, something like that, and everything is based on basic properties. They're basic properties of fitting ideals, and some combinatorics. Okay, general properties of fitting ideals. That's the key word.
What about
I don't know. That's of course the famous theorem is actually the other direction, right? From here to here for n equal 1 is a calculus problem. It's chain rule, etc. So in this case, it could also be a calculus problem, but and you can manage, to control all the computations. That's why they are using more powerful tools to go from here to here. So at some point, together with Wagner and Abel, we were trying actually to answer this question. And we were also wondering how to go, if we could go back. So we went to the literature, looked for Mader-Jau's proof, too difficult. Then we went to Grohe, Lossen-Schustin proof, even worse. So no, we declined to, we didn't continue. Yeah. So I really have no idea.
So does it mean that there's another direction for any n?
So fix some n and then.
Just for some n or for any?
Yeah, I mean, they didn't ask this, so we can, ask the question. For all, for some, yeah. We don't know. I have no idea if this is true. Yeah. Okay?
So for instance, for n equals 1.
For n equal 1 is a classical theorem. So even n equal 2, we could try, right? For some, I don't know, yeah. Okay. And so, yeah, okay, so we have this theorem. It's a very, very elegant proof. And then we started working on the second question, okay? Theorem. So this is the theorem with Wagner, Abel, Castorena, and myself. This was also last year. And, well, firstly, A is true, okay? Okay? And this I needed the matrix, right? Because to be honest, at first I thought it was going to be false, because this higher Jacobian matrix has first order derivatives, then second order derivatives, and then again first order derivatives. This 1 and 2 means the order of the derivative. So if you take a maximal minors, you are mixing the order of the derivatives. So it was not clear to me that this was going to be true in general. Right? Maybe here, in this particular case, maybe, but in general, I didn't believe in the conjecture. But actually, we started working on this, you know, with after many examples and just computations, actually. You know? Just take the definition of the determinant as sums of permutations, etc., and then you check that every summand is weighted homogeneous, and the tricky part is to show that they have the same weighted degree. Okay, but this was mainly computations, and then for the second part, we stick to the case of S equal 2. Okay, but now we can prove it for any n. Okay? So again, S equal 2 and any n. Okay, so it was also true. It's true. Okay, so last minute. Okay. Okay, I can do this. I can do this. Okay. So as I said before, this is computations. Okay, you know, many examples. Sorry. The weight is fixed. Yes, the weight is fixed. Okay. Now for the second part, actually the main idea, and this was let me say it like that, the non-trivial part of the proof is to show that the weighted degree of any maximal minor, okay, of the Jacobian matrix for n greater or equal than 3 is always greater or equal than the weighted degree of f. Okay? This took some combinatorial work. Okay, so we were able to prove this, and after that it's just the proof is actually very similar to the one of Hussain, Ma, Jiao, and Suo. These are standard arguments on negative weighted derivations in two variables. They can be reduced to this one. This is a negative weight derivations in two variables. For some complex number and some integer b. Okay, and then it's very explicit, so you just play with this and this part. Okay, so you play with this one, the weight decreases, and then that's how it starts, the proof. Okay, and some like standard arguments in derivation algebras. Okay, so that'll be all. Thank you.
So thank you very much. For next talk, I'll finish on time. So is there any question? Please.
So is there a relation between the topology of the F, the D, the monodromy, the Fan-Risco monodromy, the Miller non-verses, and the associated effect minor, you know, it's weighted homogeneous, so you also have hypersurface. With isolated singularity, is there a relation between the topology of that and the topologies of the disease?
Yeah, I mean, and I'm sure that I read this somewhere, but right now I'm trying to remember, but I don't know. I mean, we never think about these kind of questions, but I've seen this somewhere, and I think the answer should be yes. Yeah, but yeah, should look for references. Yeah.
Please.
Is there some geometrical or topological interpretation of these tau ideals?
These ones.
Yeah, right. I mean, for n equals to 1, delete the f, then it's the Miller rule. Is there some geometric interpretation?
It hasn't been done for the moment. Yeah, I guess this is a similar question. Yeah. It hasn't been done. Okay, nobody has even tried to study this. So, but n equal 1. N equal 1 is the Theorina number. Yeah. Yeah. So this is very recent, so we're still thinking about questions and all, but these are, of course, natural questions, but we haven't tried yet. Yeah.
Okay, any other question, please? Go ahead.
Is the isomorphism in the left the same one as the one on the right?
Isomorphism on the left.
The one, if something is isomorphic, then something else is isomorphic. Is the same isomorphism?
The same isomorphism as for n equal 1. You mean?
No, sorry. When you compare these two singularities,
These two hypersurfaces?
yeah, you have an isomorphism.
Yes, of algebras.
Yeah. Is the isomorphism the same guy on the left and on the right? Or not?
It is the one. Yes, I mean, yes. It's, you have here a.
But do you have the same isomorphism?
Yes. I mean, I think this. So, the whole idea is, so this isomorphism is a restriction of. No, this one is in CS0. I don't know if this is the question, but okay, let me continue. Okay, CS0. There is an isomorphism here. It restricts the. This one induces an isomorphism on the algebras, right? And so the whole idea is to prove that under this isomorphism induced by this one, let me call it phi of the ideal, f jn of f equals g jn of g. So this is the idea. That was the question? Yeah. Yes, it is. It's an isomorphism induced by the one we had. Yeah.
So it seems that there is another question there. Okay, go ahead.
Yes, thank you. No, not at all. I mean, we can give a definition for the higher Jacobian matrix. We can give a definition free of characteristic. There are some formal differential operators that need to be considered, but so no, it doesn't depend on the characteristic. Firstly, the definition of the matrix. Now, there is a result by Growell and Pham who generalizes Madher-Jau theorem for positive characteristic. Okay, it's not the same statement. They actually need a higher order version to have the statement. So I think, I think all the questions can be rephrased in positive characteristic setting. Yeah.
Okay.
This form, do you use some kind of formal change of coordinates?
Yes. There is also the work of Zhao, Chen, some other people, and because you can. So remember, we have two variables, and we take a weighted homogeneous polynomial of degree d. So after a change of variables, you can suppose that the weight of the first the coordinate satisfies this, and satisfies this, something like that. So the first coordinate is special. So after a change of coordinates, you can suppose this. Yeah. Thanks.
So one more question. If not, thanks the speaker.
Okay, thank you.
We return at 12.
Ole, ¿cómo estás?
For the first projection,
Yep.
the one that you erased, the one for n equal 1.
In the other direction.
To be related to this wall theorem, right?
Wall's theorem, which.
Projective space as the only variety which has a vector field vanishing on a hyperplane, or vanishing on an ample divider.
sé si quieres.
¿Puedo? ¿Cómo? Bueno. Lo tengo que hacer así.
A ver, intenta así.
Hola. Hola. ¿Se oye? ¿Se oye allá atrás? No. Espera. ¿Se oye allá atrás? ¿Sí? Sí, este era tu reloj.
Ya estoy olvidando.
Chico, ¿cómo estás, chico? Pero ya me perdieron mi... A ver si no te avergüenzo, Pepe, que voy a decir algunas cosas. Sí. Yo creo que sí, porque hay fotos ahí. Pero me dijeron que me esperara un poquito.
So, next speaker is Patricia Dominguez, and she will talk about Klein groups and his relation with holomorphic dynamics. So please.
Thank you very much. Thank you to the organizer. It's very glad to be here celebrating Pepe's birthday. The first part of my talk is going to be about Pepe's legacy that he has done in this institute, and not just in the institute, but in other parts of universities around Mexico. So I'm just going to talk 15 minutes of mathematics or a little bit more, but because I think it's important to tell what Pepe has done in this, not just in the institute, as I said before, but in different parts of Mexico. So this is the book who was done in his 60th birthday, and now is 10 years after the 60th birthday. So here we are again. So this is a very emblematic building. This building for the new generations and also for the people that know about the Institute of Mathematics is a really well center where when we are students, we always dream to go there to do mathematics after doing a PhD. So I was dreaming about that, and this is the building in Mexico City, the Institute of Mathematics. So there are very good mathematicians over there, and there are very nice library as well. So when we are from different universities in the country, we always want to go there to see these books in this nice library. So I was looking through the history, and it's this document which says Institute of Mathematics 1942-1987, and I was trying to see what Pepe has done since then, when he was a very young mathematician. Then I found, I'm not going to read it, this is in Spanish, but I'm going to tell you what is it about. Is it about geometry? So Pepe was saying here that explaining more or less what geometry is and what he wanted to do about it, and the goals. And one of the goals over there was to try to get a group of young people, not just doing research in the Institute of Mathematics, but in different places, states of Mexico. So this is what his name was somewhere. But also, he was writing something about group of Lie and complex surfaces. Okay, and then it's more or less what he says here is the same. He had this dream of having a group of young people, not just in the Institute of Mathematics. So Pepe, Pepe is in the poster, of course. But not just that, there was another person, Javier Gómez Moin, doing dynamical systems, and he was saying here what dynamical system is and what they wanted to do about, again, research in the Institute of Mathematics. And it's very interesting because over here, he explained why the reasons are to get young people to work in different places all over in Mexico City. So at the end, there is something, at the end, maybe you can see, but this says that there was a very small group formed by Berhovsky, Alberto Berhovsky, Pepe Seade, and Gómez Moin. Gómez Moin was written this for dynamical system. So it was the first group that, as I know, formed in 1984, I think. So it was Gómez Moin, Pepe, and Alberto Berhovsky. So I'm talking about dynamical system in different, I'm not explaining what kind of dynamical system, but it was the dream. Over here, they say the same. Gómez Moin say the same, that they want a very strong group of young mathematicians doing mathematics, not just in Mexico City, but in different parts of Mexico, okay? I think that is quite important because they were quite young and they have this dream of doing research. Not just, they didn't want to do research by themselves, they wanted to expand it, spread it on Mexico City. So when I came here after my PhD, this was the building here, the building over there, and it was not quite good in the sense that it was small, but we have a very nice palapa and hamacas as well. And it was 1999 when I came here after doing PhD. And one of the persons who said, yes, you can come, was Pepe Seade, who said, yes, you can come. There are more people working in holomorphic dynamics. Come, please. And at that time, when I was listening, Pepe, he was having this idea of expanding this building into like analytic continuation to another building. Yeah? So it's what he has done in some way. So of course there are more people involved, but what I want to say is that Pepe was one of the main forces to do it. And the idea of doing that, I mean, I'm not talking about Gómez Montt, but I also can say so many things about CIMAT, who was really small, and he was one of the forces as well in the research in CIMAT. So what we have now is you can go to the other building, yes, like an analytic continuation without going outside. Okay, so many people has been next to Pepe through all these years. I should say from 1984 to 2024 is 40 years of work. And pues, is Alberto, Santiago Lopez, Fico, Gómez Montt, of course, and Laura, who is always has been there, and Laura is over there, and he just got the prize of National University Prize in 2020. So these people are very involved in this unity of Cuernavaca. So when he was talking about young research, it was really the way he was thinking. So he's Araceli Bonifat. When I arrived, it was Araceli Bonifat and Peter Makienko. They were the people who were doing holomorphic dynamic at that time. And then I just put some pictures of the young researchers that are working in the institute, and many of them are here because the idea of Pepe and Alberto and Gómez Montt. Mm-hmm. So I just moved to another university, but Pepe has been supporting students in schools, in workshops, conferences, supported group of holomorphic dynamic, the group in my group, or holomorphic dynamic. When I came here in 1999, there were no group of holomorphic dynamics, so we started a group, and now it's a very, very strong group in Mexico doing holomorphic, not just holomorphic, and other subjects related to it. So he always has been supporting students as many as he can. And I put here because Pepe is over here, yes, Santiago is over here, and here they had 80 students with scholarships to come here. So what I want to say is that since I met Pepe, I met many of you because of him, because there was very nice conference. He wanted to get a researcher from all over the world to come here, and he wanted this Unidad Cuernavaca to be recognized in many places. So I think he has achieved that. He has achieved that because there is a group of holomorphic dynamic, not just in the institute. We are in Puebla, Tabasco, Guanajuato, Ciudad de Mexico. So we have this group. I'm talking about the name of my group, which is holomorphic dynamics. And also, he has got so many prizes. So he got the prizes Ferran Suyer y Balaguer, Salomon Leche's American Mathematical Research Prizes. So he's over there getting his prize, very handsome and very proud of it. So what I want to say that really Pepe has been supporting in many ways researchers, students, and groups in Mexico. For instance, in Puebla, when I'm working on, Pepe has projects, and the money is supposed to go to just Institute of Mathematics, but that is not true. We have got 3 postdocs with the project of Pepe, with money of the project of Pepe, paying for 2 years each one. 2 of them are now not professors, professor is different in USA. They are researchers which are working now with a time which is how to say, tiempo completo, full time, yeah, full time. So that is the nice thing I wanted to say to Pepe, is we really appreciate what you have done, and we really like you. Would you have groups all over states of Mexico, in Yucatan as well. He has a group. So, and this is the monograph that he was winning the prize, and it's complex claim. It says complex claim groups. So now I'm going to talk a little bit of much, and I will leave Pepe, because I think maybe he's embarrassed of what I'm saying, but I think it's very important to say this to the group of holomorphic dynamics. So I'm going to say what is the relationship between Kleinian groups and complex dynamics. I'm not going to go into the details because we are short of time, but many of you know what is a Kleinian group, okay? So instead of you don't know, the youngest people they know, so the definition is over here, and you can read it, okay? So this Kleinian group not started, but has its roots with Klein and Pomerenke, and Poincaré, pardon, Pomerenke is another, and Poincaré. So let's gamma be a Kleinian group, omega gamma is ordinary set, and delta gamma is limit set. So every Kleinian group has this limit set and the ordinary set. Okay, it's divided, it's a dichotomy that it has. Okay, some properties of that is the ordinary set is open set, sigma invariant, which means this. See? This is an element of the group. The limit set is closed, set invariant. As you see, this is the complement of this, and this is complement of that. Okay. So we have, if you have a sigma be a non-elementary Kleinian group, the limit set is a perfect set. In particular, the limit set is an uncountable set. Okay. The ordinary set has at most two invariant components. Is what, when you study Kleinian groups, these properties go. Is what the student has to work on. The fourth is the number of components of the ordinary set is 0, 1, 2, and infinity. Okay. Okay. I'm going to go into a residual set, a definition of residual set. The residual set was investigated by Abikov in 1972. He defines this residual set for Kleinian groups. They think, at the time Klein was working, they were thinking that it was empty set. It was an empty set. So what is a residual set? So the residual set of the group, denoted by this, is defined as the limit set removing the union of the boundaries of the ordinary set, is what it says here, where this gamma I are the components of the ordinary set. In other words, the residual set consists of those points that remain after we remove the boundaries of the component of the ordinary set to the limit set. Okay? So this is the definition who was done by Abikov in 1972. So as I said before, they believe that this set was empty always. But Abikov constructed two examples in which of Kleinian groups that it wasn't true. So it was not empty. So what is it? Now I'm going to switch to holomorphic dynamics. And then holomorphic dynamics was, well, of course, it was started by iteration of functions, but the main people who were working on that was Fatou and Julia. And then we have a rational function, at least more rational function with at most degree 2, or to be better, more than degree 2. So we are going to denote rational functions by R. The Fatou set of F or stable set, what, as we say, denoted by like this, is the set of all points such that the sequence of iterates is well defined and forms a normal family in some neighborhood of set. Well defined, we don't need this part because it's always done when you have a rational function and you iterate it by a composition. It's always a rational function, the composition. So, but anyway, I wrote it. The Fatou set is, I wrote it here in this small definition. And the Julia set is the unstable set denoted by JF, and it's a complement of Fatou set. What we are looking at is that there is a dichotomy of the sphere as well, as in the Kleinian groups. Yeah? So the residual, and now I'm going to define the residual Julia set for these functions. The residual Julia set of Julia set, denoted by JR, is a set of points, Julia set which do not belong to the boundary of any component of the Fatou set. So the points are called varied points, and the components, of course, are called varied components. So some properties, if the Fatou set has a complete invariant component, then the residual Julia set is empty. This are properties of the residual Julia set. If there exists a boundary varied component in the Julia set, then the Julia set is not connected. If the residual Julia set is empty, then the residual Julia set is complete invariance, dense. The Fatou set, sorry, is complete invariant. If the Julia, no, sorry, I'm saying that wrong. If the residual Julia set is not empty, then the residual Julia set is complete invariant, because in Julia is always invariant, complete invariant, and it's dense. The Julia set is dense, so this set is in the Julia set. And also it's uncountable infinity. Okay, now you have what is the relationship between these two areas? This is called the Fatou-Sullivan dictionary. And the Fatou-Sullivan dictionary relates dynamic of rational functions with degree more than 2 and Kleinian group non-elementary and finally generated. Finally generated is that it has a finite generators, the group. So what are the analogies? Julia set is the limit set. The Fatou set is analogy with the ordinary set. If the Julia set is closed set, non-empty, complete invariant, then the limit set has the same properties. Yeah? The set of repelling periodic points is dense in the Julia set. The set of fixed point of all loxodromic elements is dense in the limit set. The number of components of the Fatou set is 0, 1, 2, or infinity. Number of components in the ordinary set is 0, 1, 2, or infinity. The Fatou has at most 2 complete invariant components. The ordinary set has at most 2 invariant components. We cannot talk about complete invariant. The 7 is the boundary of complete invariant components is the Julia set, and the same happens for the ordinary set and the Julia set. And the 8 is residual Julia set in Julia set. The residual set in Julia set is the residual set in the limit set. So this is the relation that there is between Kleinian groups and holomorphic dynamics. I should say that going from here to here is not possible through topology or geometry or any other, as far as I know, any other area of mathematics. It's just analogies, Okay. So some results of Kleinian groups, which have been copied in 1972, it has these 3 theorems. And I was looking at these theorems, and what worries me is that the residual Julia set for holomorphic dynamics was given by, the first example for holomorphic dynamics was given by McMullen in 1988. So it's not very old person that, it's not very old, the residual Julia set, as you see. So I always try to see what is the relationship between the residual Julia set to results between these 2 areas. And well, Arbikov has this theorem, theorem 2 and theorem 3. What is a non-function group? Non-function group is a finitely generated Kleinian group. with a component which is invariant, and connected component invariant. Invariant component, connected component. So we have, he gives, with these three theorems, he gives existence of this set in the Kleinian groups. Some results of holomorphic dynamics that was given, the first one of existence of the first example given, the first example of a residual Julia set for rational function, I say that it was given by McMullen. But Bierdon gave the first theorem of existence for the residual Julia set in the holomorphic dynamics. And as you can see, these three theorems with the previous one, they are similar in some sense. So the idea of this talk is to tell you that the relation between these two areas, so there is relation between the area of Pepe and the group of holomorphic dynamics that we have in Mexico. And if we study Kleinian groups and very interesting results, maybe can be analog to some of the results in holomorphic dynamics or vice versa. So, but you are thinking about what this look like? What it look like? How can I see this? Because buried means buried. Buried is deep, deep. Sorry, deep that we cannot see it. Okay. So I'm going to. I'm not really working rational functions. I work in entire functions, which are analytic functions from the plane to the plane. Also, I work with transcendental meromorphic functions, which are analytic from the complex plane to the sphere. And also work on dynamics of meromorphic functions outside a compact countable set of essential singularities. So, and the definition of Abikov can go through all these class of functions. It's the same definition. It's the same definition. So I'm going to give you an example of a buried component. As you can see, if we can see the buried component. So if we take the family, this is an entire family. Lambda is a complex plane. So if we take this family and we take lambda equal to 1, then what we have is the Julian Fatou set. There is a dichotomy. So it was proved that for this function there are two invariant domains, D1 and D2. They simply connected, bounded, okay? And also, what it was proved is that any point, this is a parabolic point, I'm not going to say, but the parabolic point is, or inside these domains, the points inside this domain converges to the point in the boundary, is what it says. So there are two, as I say, two invariant components in the Julia set, in the Fatou set. There are no more. And then what was proved is this, from some point, the iterations of any point here goes to infinity. Y always not zero. Okay? And from here the same. Okay. So because this family is symmetric, then what you have, this picture we can see this picture over here as well, and so on that side, and from this side you can have this. This is p minus p over 2, and this is pi over 2, I think. And the critical values are inside one of these. There are just critical values, minus 1 and 1. So this is what we have. And if we continue doing iteration, so we can see, we can take on this whole picture, and we can put it in this way. Because, so what we have is this picture. We can see this picture over here, okay? And also over here, since the sign family is symmetric and it's periodic as well, okay? So we have this picture, and if we took this picture and took this one, so we can see this, and over here we can, so on, okay? So we can think that all of this is full of components in the fatu set. See? The boundary of this component is exactly this one. The boundary of this set is as you can see, the fatu set is bounded, and any component over here, because this is invariant, any component over here under iteration goes to here or to here. It cannot go another way, okay? And we can see that Julia is connected. We can prove that Julia is connected because we can always continue. So there is no discontinuation of the boundary of this set, okay? Okay, how can I see these buried components? Okay, suppose that we don't have any buried point in the Julia set. There is no that exists. So I'm going to take a point over here, and because if the point is not a buried point, it means that it can be in the boundary of a component of a two set. So because this is no residual point, the buried point, I can draw here a component, and it should be in the boundary of a component. But this is a contradiction. Why? Because if I take this component under iteration, it goes to here or here. Okay? If it is going inside, these points, I forgot to tell you that this belongs to the Julia set. Okay? And if you take this component, under iteration goes from to here or here. And if you go inside, it's contradiction because this is a point in the Julia set, and this is fatu set, and it's simply connected. It cannot be done. It cannot be true. Okay? And if it goes to the boundary, if under iteration it goes to the boundary, this is bounded. This point is bounded. So, but points over here, they go to the infinity. So, contradiction. So it means that this point has to be a buried point. And if this point is a buried point, it means that there are many points the same, and you have a buried component just with the imaginary axis, axis. So this is an example in the entire function. So we can carry on many things of the Sullivan's dictionary to, not many things, but we can be very carefully about what can translate to the entire functions, meromorphic functions, and functions with the meromorphic outside a compact countable set of essential singularities. Okay, so let me see how it go. Okay, so this is what I wanted to tell you. So we're still working on that in residual Julia set, but not just that. We're working in another kind of components in holomorphic dynamics. And from the group of holomorphic dynamics in Mexico, we wish you, Pepe, a very nice happy birthday.
So thank you very much. So is there any question? Please.
So I have two remarks. On the first part, perhaps you forgot to say that also Pepe was director of the Institute of Singularities in Mexico City for 8 years, and he did a wonderful job. And talking about expansiveness, after he did that, right now, he is the president of the Mexican Academy of Sciences. And as you know, this is a very difficult time, so he has confronted the director of CONACYT because of his bad
behavior.
So in that sense, not only expansive, but valiente.
Brave.
So
Brave.
And then also, on your dictionary, perhaps I overlooked.
There are more properties. I just don't.
You're very impressed by Abikov, but there's this Alfor's finite.
Oh yes, yes.
Say that the regular set divided by the group is a finite union
Yeah.
of finite Riemann surfaces, and then on the other hand, is perhaps Dennis' contribution to the main contribution to this holomorphic dynamics, and it's called Sullivan's non-wandering.
I didn't want it to write down more properties between the two of them because it's a big dictionary now. It has continued growing up. So because I wanted to talk about residual, Julia said I had to stop in some time and not saying what you say. But thank you very much, and that is true. But many of you know that Pepe has been a very nice nice director of the Institute of Mathematics for 8 years, as you say. And give congratulations to Alberto Gomez-Mon, Pepe as well, because indeed we have several groups spread on the Mexico City from different areas of mathematics, thanks to you.
So, thank you very much. So, thank you. So, we'll continue in 5 minutes. So maybe I also, because I have to leave tomorrow, I want to mention that I knew Pepe since 44 years ago. So I mean, at this time when he has a lot of, we make some plans. And by the way, there was also another person that was at this time involved. It was Sebin Recillas. It was also new at the same time as Pepe. No, unfortunately, he's not here. And okay, so I'm very honored to be here and remember this time. When he was finishing the PhD, as I myself. So okay,
yeah.
Thank you.
Thank you.
So continuing maybe 5 minutes. Es la hora, pero bueno. No, 10 minutes. 10 minutes. We continue in 10 minutes. Tú no te acuerdas.
Sí, sí. Yo ando buscando más fotos de Pepe joven, esa me la mandó. Parece. Digo, ¿tienes fotos?
Sí, claro.
Y anduve buscando en internet y no anduve buscando de la palapa bien. No encontré.
Ya.
Este es de Ángel. Gracias.
¿Ya? Bueno, sí, yo creo, ¿no? Sí, se escucha. No. A ver, bueno, sí, sí se escucha. ¿Sí? Yo creo, ¿no? ¿Sí? Bueno, si no, grito. Tranquilo.
Muy bien.
Ah.
Next speaker is Aurelio Menegaz, and we'll talk about observation for Mars and Singularities. Please start.
Well, so thank you very much for the opportunity to be here. Thank the organizers, and it's always a pleasure to be here with you in Cuernavaca. Well, I want to say that I met Pepe in 2007. Then 1 year later, I came here to do my PhD under his supervision. And since then, well, I have learned a lot. I am still learning a lot with Pepe. Thank you very much for all your advices, and please keep advising me. So congratulations, and thank you very much. Today I want to talk about something that I'm still my idea is just to share with you some things I'm still trying to understand. So it's some recent things I've been thinking about. So first I want to say some background on the Milnor-Ley fibration, because I will talk about some kind of generalization of these ideas. So this is very classical when you want to study the local topology of singularities. So this is like one of the pillars, one of the main to study these objects, these singularities, is the Milnor-Ley fibration. So we start assuming that X is some term of a complex analytic space in Cn. So this is like the first setting. And F is a function, a complex function germ on X, right? So then have this very famous theorem due to Milnor 68 and later to Ledon-Trunk 76 for this general context when X is any complex analytic set. So we have this Milnor-Ley fibration, which basically tells you that locally, so if you look very close to the origin here, the function F restricts to a topologically locally trivial fibration. Also, this is this very classical theorem in the field.
First case,
yeah.
Defined by what function?
X? No. X is any complex analytic space. Okay, and then we have a function defined on X.
In the state that you have F.
In the state that you have F here. Yeah. The function is defined on X. X is any, right?
So what's the generalization of Lay?
No. This is, because Milnor proved first when X is Cn. Then Lay.
No F there.
Milnor did it when X was smooth.
Yeah.
Now, Milnor did it when X was smooth. Here X can be any singular variety.
Yeah. Right? So this is by Milnor and Lay. I'm combining them together. Yeah. Okay. So we have this fibration. So the fiber of this locally trivial fibration is what we call the Milnor fiber. And it's a very good way of studying the singular one, because you have this smooth manifold approaching the singular one. So you can study the topology of this Milnor fiber and associate it with the singular variety you want to study. So this is one way of studying this local topology of singularities, right? So this is very classical, works very well. In this setting, we have a function, right? So what about, the question here is, what about more general maps? So suppose now we have f, a function, not a function, but a map germ. So it goes from x to, say, ck for some k. I don't know, k equals 2 or whatever. So then with k bigger than 1. So then what can you do? Like in general, you don't have Milnor fibration like the previous one. So you cannot talk about one, in general, about one Milnor fiber. So, and the problem is that, well, you do have some positive answer in some case. So when f from Cn to Ck defines an isolated complete intersection singularity, then you have the theorem working. Eh?
That theorem is due to Ham. Liga has it in the book, but the theorem is due to Ham.
Okay, so, yeah, okay. Sorry. Okay, so due to Ham.
In German.
Yeah, okay, so in some cases you do have a fibration theorem like this, but in general you don't. So the problem, basically we have two phenomena can occur. The first one is that there may be fibers, let's say, they are not fibers because it's not a fibration, but f minus 1 of t for t very close to 0. This object can intersect the spheres, even if you take very small spheres of radius very small, this intersection can be not transversal. So this makes everything fail. So you cannot have a fibration if this happens. So
what if you distort the sphere to the limb source?
You are going to have this kind of phenomena occur. So you cannot avoid them like by doing this. So this is one problem, because basically the theorem comes from because of the transversality, because then you have on the boundary you have everything smooth. So, but this fails in general, so there's this kind of problem. And the second kind of problem that you may have is that the image and or the discriminant of f may not be well defined as adgerms. This was pointed by Ribeiro Santos, who is here also, and Tibar in 2019. So they described this phenomena. So you cannot talk about discriminant of f as a germ. And this makes everything much more complicated. So you cannot treat the discriminant like in the sense of germ, because in general they give many examples where this happens. So you have these two kind of problems.
Are they algebraic geometry examples?
Yes, right. I think yes, right. Yeah. So yeah. So I didn't bring the examples. Sorry for that, but this can happen, and this is a big problem if you want to generalize this Milnor fibration.
Are those examples also in the complex case or only in the real case?
In the complex case also. Yeah. If you have k bigger than 1. Yeah. Yes?
I think you can just take the blow down from, or the blow up of the point into two space and take it there, and then you will get an example of something.
There are ways, Yeah, you can do some, So what? Well, the things that you have these two kind of problems, let's say, and how to deal with them. No? So the idea is the following. So let me define what we call this transversality property. So you consider a witness stratification of X, this complex space, and this S could be maybe real analytic or subanalytic. Everything works the same, right? So you take a witness stratification of X, and then you define the singular set of F relatively to this stratification. Of course, everything will be relatively to the stratification you are choosing, of course. So this is a germ set. There's no problem for this. And then you take some representative F and epsilon bigger than 0, and then you look at this restriction. Okay, this is very well defined. And then we can give the definition. We say that F has the transversality property, TP I'm calling, relatively to the stratification F, if you have this transversality, the intersection of the fibers with the spheres, sufficiently small spheres, you have the transversality every time. So this is what we call the transversality property. In general, it doesn't occur. Sometimes it does. And this definition doesn't depend on delta, the discriminant set, being well defined as a set germ, because you are fixing epsilon. So everything works. You can define this transversality property in this stratified sense. And then the result is that, okay, if F has this transversality property, then first thing, the image of F is well defined as a set germ. So this problem won't happen if you have this transversality property. And then you can do a Milnor-Ley fibration type theorem over the image of F, which is well behaved as a germ. So you do have this Milnor-Ley fibration. And the fibration above doesn't depend on the choice of epsilon. So everything works fine if you have this transversality property. Okay, but it's difficult to check if you have this happening. No? It doesn't matter. Both. Over R, yeah. And X can be subanalytic. So that's the theorem. If you have the transversality property, everything works fine. So I'm going to give you just like the idea of the proof of this. So first, we need this lemma, which says that for every epsilon 1 in between 0 and your first epsilon 0, so you have these two radii, epsilon 0, epsilon 1, then there exists some delta bigger than 0 such that this intersection is contained in this intersection. So here you have, this is the big ball, then you project this by F, the intersection with this sufficiently small ball here is contained in the image of F on the smaller ball, B epsilon 1. Okay, so, and this lemma will help us to prove the theorem. So in order to prove the theorem, the difficult part is this one, to construct, you can construct a never zero integrable vector field V on this object. So you take the image of a sufficiently small ball B delta, you remove the discriminant relative to this fixed radius epsilon 0, and then you intersect with the big ball minus the small ball. Okay? So we are going to construct a vector field here which is smooth and tangent on each F minus 1 of T intersection with the corresponding strata. So the vector field is smooth and tangent on each object like this, and it is transversal to each sphere point inwards. So you can travel along this, the flow corresponding to this vector field. And then it's easy, because then once you have a point T here, you take some x in the fiber, the corresponding fiber, and then you travel along the corresponding integral curve, and then you are going to arrive at a point y here in this f minus 1t, is the same t, of course, because the vector field is tangent to this. So we are going to arrive at some point here, but in the smaller ball. Right? So this means that this point t lies here, which is contained here, so it lies here. So this gives you this inclusion. It's just the, so once you have the vector field, it's very easy. So with this lemma in mind, we can prove the first part one, which is the most difficult part of the theorem, the most interesting part, I think, that the image of f is well defined as a set germ in this case.
So what's the alternative? What is it if it's not a set germ?
So what is not, sorry?
What do you mean that you read both sides?
What do I mean by what? Sorry. The image?
Is not well defined as a set germ.
Because maybe if you reduce the ball, so you could have something like, so suppose you look at the and you apply the function f, and the image could be something like this. And then if you take a smaller ball, the image could be this, something like this. And the other was, you know, so it's not as, yeah? So that's what we want to avoid, because then nothing will work. So, yeah, I'm late. So we have this, so with this in mind, with this lemma, you can prove the theorem. Sorry, I'm going to skip. But, yeah. So, okay, how can we get some criterion to decide if your function defined on your x has this transversality property, so everything works? So this is one criteria. It's very similar. It's like a generalization of a criterion given by David Massey in the smooth case. So it's not totally original, but it's extending this more general situation. So the criteria is the following. If you have a function like this, then it has the transversality property. If and only if you can find some epsilon 0 small enough such that for any other epsilon smaller than this one, this intersection is either empty or just the origin. Okay, so this is a criterion. As a corollary, very immediate, you have that if the singular set of the, sorry, I didn't say what is this function, it's this map. Okay, so it's just f and the distance squared. So if you have the only point in the variety defined by f, which lies on the closure of the singular set of this map phi minus removing the singular set of f, if this is either empty or just the origin, then you have the transversality property, and with this corollary you can make a lot of examples, right? So this is a criterion. It's not a necessary condition. Sorry, this is a necessary condition for you to have this kind of transversality property. And then, well, this, okay, it works, it gives you the fibration, but then the next question is, can we do more? Because in the smooth case, right, or in the case of a function, f, just from x to c, this transversality property always happens, and this comes from the fact that these functions, they have the tone property. This is a theorem due to Hironaka, and it says the following. So if you have a k-analytic map germ from x to k, then there exist witness stratifications of this space, okay, and of this, such that the function takes strata to strata, and the restriction of the function to each stratum is a submersion. Okay, so you can always do this, and then you can define this property, the tone property. So the stratification is said to satisfy the tone AF condition with respect to F if for every sequence of points in a stratum converging to another one, in the closure of this big stratum, thus you have the corresponding sequence of tangent spaces. It converges to some limit t, and this limit t contains the tangent space of the point on this smaller stratum. So this is the tone AF property, and this tone AF property gives you, in particular, as a consequence, it gives you the transversality property. So that's why everything works fine. This is how Le proved the Milnor-Le fibration theorem in general for X and any complex analytic set. So everything comes from this property. So the question is, okay, can I still have this kind of tone AF condition for these maps now, where maybe the discriminant set is not even a well defined as a germ, or the image of F is not defined as a germ. So this is the next natural question. And then, well, you can do the same thing for this new setting. So you have F from X to K, a K analytic. K is either R or C, right? And you suppose that the discriminant is well defined as a set germ. If you do this assumption, then everything works fine, and you have fibration. You have the tone property implying the fibration, right? So if you have this situation, then you can take stratifications like this, right? And then if you can do this, then F has the transversality property relatively to the stratification of X. So this works fine. It's not very original. It's basically a mimic of the original one. But the problem is that you need this, right? That the discriminant is well defined as a set germ. Otherwise, this won't make sense. So that's the problem regarding the condition I of the theorem. In the case when F has an isolated critical value, then this is satisfied. Okay? You always have this stratification. However, when the discriminant is an arbitrary subanalytic set germ, it is not clear, at least not clear to me if this holds, but certainly when the discriminant of F is not well defined as a germ, then this won't make sense, of course. Then we need to do something, and then we can come up with this new alternative notion of regularity. Like the idea is to replace this tone AF condition so that it makes sense even when the discriminant is not well defined as a set germ. So how do we do this? Well, we define, we take stratifications. So we have the function F. You take a Whitney stratification of X. Then this is well defined, the singular set, with respect to this stratification. By Whitney, you can refine this stratification in such a way that the V of F, so the zero set of F, intersection with the singular set of F is a union of strata. Sigma F is also a union of strata. Each stratum on this finer stratification that is not contained in sigma F has this form, is a previous strata removing the singular set. So you can do this. And then you can define this definition makes sense. This definition will be well defined. We say that S prime, the Whitney stratification, this good one we construct on X, is T-regular with respect to F if for every sequence of points xi in one stratum S alpha prime not contained in the singular set, converging to some point X on the variety of F, except 0, such that the sequence of tangent spaces has a limit T, one has that T contains this tangent space at the point X on the corresponding stratum. No. So this makes sense because then you have all the conditions that you need for this to make sense. So this is well defined. And the theorem now, the good one, let's say, the one that works for this more general set is the following. So suppose you take f a function on x, like before. So if you can find, if there is a Whitney stratification of x such that the induced stratification S prime is T-regular with respect to f, then the function f has the transversality property relative to S. So everything works fine. So that's the theorem. Yeah, that's so when, that's the next question. When can you have this, right? But we are getting there, yeah? So, but if you have this, then you have the transversality property, everything works fine, right? So just one remark that when you have, when f has an isolated critical value, then it's nothing new. This coincides with the tone property. So it's an extension in this sense. So, but when, and if the v of f is 0, then f is T-regular. But this is very strong condition, but then everything works. So just a remark. Right. So with this, so now I'm going to talk about some consequences. No, in some particular cases, when do you have all of this happening, right?
Before you go into this consequence of mechanisms, does it have something with the finiteness theorem of the topological types of the maps?
I don't see how. Maybe I don't know. I'm still, as I told you, I'm still.
So that if you have a sort of set of maps such that they have this transversality property, then you have a topology of the map. You can describe it using this kind of vibration, right? And then it should be stable. And if you just compare that with the Nakai counterexamples, where you have this kind of infinitely many topological types, where you have five families of what you like.
No, I don't know, Lev, but well, we can talk. Yeah, I don't follow. So, so as a consequence of this, like immediate, we have an extension of Loyenga's theorem, which is the which is not. It's that theorem, which say so is the consequence is the following. So if you have f from x to kk, like before, then if this happens, if v of f intersects the singular set of f only at the origin, and we have many examples of this, then the induced stratification S prime is T-regular. Then, so everything works. In particular, f has the transversality property. The image then is well defined as a set germ, and you have a Milnor fibration well defined. So everything works fine. So yes. Yeah, but I don't know if only in this, I don't know.
Yeah, well, but finite is property. Exactly.
Yeah, let me just finish because I have 2 minutes, and then we discuss. Okay, sorry. So this is one consequence. The other consequence I want to talk to you about, because it's related to some work of Pepe and Pichon in 2008. So it's the following. So it's a particular situation. Now suppose your X is a complex surface, okay, with a Milnor stratification S, and you take two holomorphic functions defined on X, F and G, right? Complex function germs, and then you consider this what they called mixed function germ, is FG bar. So you take the complex conjugate of G and you multiply F and this G bar. Okay, so you have this non-holomorphic function defined on X. It's very interesting. They study a lot of about these functions because the variety defined by them is complex, right? So it's the same as Fg minus 1 of 0. So it's complex. but the function is not. So it's a very interesting family of mixed functions. And they proved that if x is like this with an isolated singularity, then FG bar has the tone property, provided that F and G have no common branch, so that FG bar has an isolated critical value, right? So under some nice conditions, in particular if this has an isolated critical value, then this has the tone property, so everything works. So you have the Milnor fibration, you have the transversality property, everything will work fine. The image will be well defined as a Seade and so, but you need this hypothesis, right? Isolated singularity on X, on the surface where everything is defined. And well, as a consequence of what I've been talking to you, you can extend this, so you can remove this hypothesis. So if X is any complex surface with arbitrary singularity and FG bar is like before, with an isolated critical value, and both F and G have isolated singularity relative to S, so everything the same context, then S satisfies the tone property. Because we can show that F then satisfies this T regularity condition, which in the case of an isolated critical value is equivalent to the tone EF condition. So everything works fine also in this case. Yeah, and muchas gracias. Thank you very much. Congratulations, Pepe.
So thank you very much. So there is one or two questions? No? Then, Pepe, you have something to... But you want to say something?
Oh, yes, I remember. No, just, as you know, tomorrow night we have this visit to the Palacio de Cortés, which has very beautiful wall paintings by Diego Rivera. It will be a special. It will be especially open for us. It will be closed at that time. They will open it for us. Then we'll have a mezcal tasting and a beautiful concert of Mexican music at Palacio de Cortés. But we need to. We must be. That starts at 6:30. 6:30 we must be there. But we need to know today who is coming. And we have to ask for 200 pesos each for certain things we have to pay. And we need to know today to organize ourselves. So please do it with Liz, the secretary. Thank you. Sorry? Yes, you can. No.
Okay. It's clear. So we resume in 4 minutes. Because we have to go for lunch.
Nacho, hay otra plática hoy. ¿Hay otra plática? I just see it.
Let's be brave.
4 minutes, get out.
Yo la acompaño. I keep you company.
So next speaker is Lev Bilber, but he's disappeared. Lev? Ha desaparecido. Lev. ¿Alguien ha visto a Lev Bilber? Estamos esperándote. ¿Eh? Pero ahora hablas tú.
Ya.
Adelante.
Sí.
Sí, sí.
No hay
Sí, ahora no lo darán. El puntero.
¿Quién fue el anterior?
Aurelio.
Tienes el control.
Adelante. Tienes que ponerte esto.
Micrófono.
Y el control será esto de aquí, ¿no?
Puede verificar si funciona.
Eu acho que você vai para o seu microfone.
Sim, está certo.
Tienes 5 minutos menos por llegar tarde.
Muy bien.
Vamos a darle
está
5 minutos.
funcionando.
Vamos a comenzar con 5 minutos más.
Bueno.
Será que você pode fazer uma troca? O microfone está aqui.
Sí. De acuerdo. Muy bien.
Então, será que você bota aqui nessa?
Next speaker is Lev Bilber. So, you can start. The title is here, so please start. Javier.
So, do you hear me, right? Okay. So So I would like, first of all, I would like to thank the organizer for inviting me. And I really just started to think how many times I visited Cuernavaca. And the point is, the answer is mainly infinity. But maybe 5 or 6 or something like this, that it is over infinity, let's say. And the reason of my talk, what I really wanted to do, I wanted to make some survey of the Lipschitz geometry of the surfaces. And this was motivated actually by Pepe, because Pepe asked me to write this kind of chapter for the handbook of singularity theory. And when I started to write it down, just together with Andrei Gavrilov, we really realized that the subject that we are writing is somehow developing. And basically, And basically what happens that what I will be telling today, it is related to this chapter, right? It is basically based on the chapter. And then it is what kind of my present and congratulations to Pepe, because he really stimulated us to do that. Okay, and this is another stimulating picture. That it's since I'm from the northeast of Brazil, it's just for you how it looks like. So that where the majority of the theorems that I was talking about were done. It's just near this kind of beach. Right? So then I'm talking about the Lipschitz geometry of singularities. And all the sets that I'm going to do to describe are supposed to be semi-algebraic or subanalytic and maps like also. And sometimes I will be talking about definable sets on some polynomially bounded to minimal structures, but for someone who doesn't know what it is, it's better not to just to suppose that everything is semi-algebraic or subanalytic. Okay? And then the Lipschitz geometry, oops. I don't know what happens. You have any idea? Okay, and then we consider the singular sets as metric spaces, right? We consider everything as metric spaces. And what kind of metrics do we have? We have 2 natural metrics. One is the outer metric, just the ambient distance. And another one is the inner metric, which is the length of the shortest of the shortest arc connecting 2 points. And then the set is called normally embedded.
The length that's computed in the
Sorry?
The length that's computed in the ambient.
Yeah. There is ambient, and then there is inner, where we compute the length of the arcs who live in the sets, right? And it is, yes, it's related to the ambient ambient Riemannian geometry. Yeah, it's ambient length, but it is not really the ambient metric. Okay, so then we have the set is called normally embedded or Lipschitz normally embedded if these 2 metrics are by Lipschitz equivalent. It means that there is a by Lipschitz map from the same set with the first metric and to the same set to the second one. Okay? And the majority of the things I will consider are just surfaces, real surfaces. Real surfaces, it means the definable 2-dimensional. And I always will suppose that they're pure 2-dimensional sets in the lives in some out to the end. Okay? Then we have 2 natural metrics, and then we have 3 Lipschitz geometries. The first one is, or let's say 3 Lipschitz geometries or 3 Lipschitz classification problems. Then the first one is a classification with respect to the inner metric. Another with respect to the outer metric. And the third one with respect to the ambient metric. This ambient equivalence, that means that the map, the bi-Lipschitz map, is extended to the ambient space. Okay? So that we have inner equivalence, outer equivalence, and the ambient equivalence. Okay, and then who are the standard?
There are two ambient equivalents.
Sorry?
There are two ambient equivalents. There's only one.
One. So that there is outer equivalence, right?
I understand the first two, but the second, there are two metrics you can put on X.
Yeah. And what?
So if they're ambient equivalents,
So that
actually is the inner.
there is, so that, okay, you have the outer equivalence, right? And the sets are ambient equivalents. If there is a map from the ambient space.
No, I can read it, I understand it. I'm just saying there are two metrics on the subspace in our discussion.
Okay.
And one, there's an automatic sentence.
Yeah.
I'm saying on logic, but I
Yeah.
can't quite do it.
Mhm.
I'm asking you to do it.
No, but let me talk about these three. Okay?
Why is it not four?
So what is the fourth? That
There are two metrics on the subspace.
on the same set, right? On the same set, and right. But actually, I consider the metrics that somehow natural, that they are the inner metrics or ambient or outer metrics defined from just restricted from the ambient set. Okay. So that I consider
I'm not communicating, it's okay, I'm not communicating, it's fine.
okay, that I consider a set, a semi-algebraic set that lives somewhere in Euclidean space, right? And
No, I'm reading the slide. I'm asking a question about it.
okay, that maybe I didn't understand correctly, or maybe we'll come back to that in the end of my talk. Okay? Yeah. Yes. From the set to the set. No. Two means that there is that you have an abstract metric set, metric space. No, but 3 and 2 are different things. Okay, that's yeah.
The Lipschitz constant is on all of our maps. So 3 implies both 2 and 1.
3 implies 2 and 1. But 2 implies 1. But 1 doesn't imply 2. And 2 doesn't imply 3. This is what I say. The 3 implies 2 and 1. Okay? Could I continue? Thank you. So, and then I consider some standard.
2 only implies, 3 only implies 2 and 1 if you're assuming it's Euler's equivalence using the inner method. But it might happen that there's something that where the ambient Lipschitz map induces a bijection on the weaker method. So, see, there's some logical point here, but it's a little too complicated.
Okay, maybe I'm somehow missing this point. But again, you have a set that lives in just a semi-algebraic set that lives somewhere in, by the definition, lives in some Euclidean space, right? Then what do you have on that? You have a natural outer metric, you have a natural inner metric, right? 2 metrics. And then I suppose that the inner metric is coming from the ambient space. Okay? And then I have 3. I don't see any more. Okay?
No, it's okay. It's not okay, but it is okay.
Okay. Otherwise, I will
Keep going.
I will not succeed. Yeah. Okay. Then, who are my standard objects? This is the standard Hilbert triangle. This is a semi-algebraic set, a subanalytic set given like this. Then there is a horn that it is a revolution surface of cusp, right? And the Hilbert triangle is something who is equivalent, by Lipschitz equivalent to the standard one, and the beta horn is somebody who is equivalent to the standard one. Okay, so there are my players of the game. Okay, so then let me start from the inner metric. It's the oldest theorem on this direction, that if you have a semi-algebraic surface with isolated singularity and the connected link, link means at everywhere the intersection with the small sphere. And then there is some beta such that our set is inner by Lipschitz equivalent, inner, to the revolution surface of the standard beta cusp. Okay? So that if you have somebody with the isolated singularity, by the way, the first triangle I don't consider it an isolated because it have boundary arcs. And then just everybody who looks like this from the inner viewpoint, looks like this. So this is a result on this direction, so that inner metric looks the most simple of the everybody. And let me just go a little bit further. Just first of all, there is a normal embedding theorem, just that I proved together with Tadeusz Mostowski, that if you have a compact semi-algebraic set, then you can re-embed it somewhere to the some r to the n, such that it is inner by Lipschitz equivalent to my initial set, and this new set will be normally embedded. I use the notation L and E because somehow Walter Neumann and Anpichon, they somehow forced me to use L and E instead of just normally embedded, but and now the usual terminology is L and E, but sometimes I will use this thing like normally embedded, okay? And then finiteness theorem. This is that if you consider a definable family, or let's say subanalytic family, then there are finitely many outer Lipschitz equivalent classes in any kind of finite dimensional definable family. And this is the finiteness theorem, and you probably observed that I was asking several speakers here, what about the finiteness theorem? That we have the finiteness theorem for the sets, and we don't have the finiteness theorem for maps. And this is, up to now, it is still confusing for me. And then there is another theorem about curves in terms of complex curves that I just used 3 different authors. Of course, the first for Bernard Tessier and Frederick Palm, that they proved that 2 germs of a reducible complex curve in C2 are ambient Lipschitz equivalent if and only if they are outer Lipschitz equivalent. It means that they have the same Puiseux exponents. So that outer Lipschitz equivalent, topological equivalence and ambient Lipschitz equivalents are the same. Why I just don't refer only to Feynman Tessier, because there is a proof of Fernandez, and the proof of Fernandez was totally different. Because Feynman Tessier, they used the tools that similar to what was explaining today in the morning. It was extremely powerful tool, but at least for me, a little bit too algebraic for the Lipschitz geometry, and the Fernandez proof was just totally Lipschitz geometric. And the Neumann-Pichon, they extended the proof, yes. Yes, exactly. That topological equivalence, it means that they have the same carousel. Yeah, and to the same, that if you consider just one branch, right, then you have this kind of iterated knot structure. Iterated knot structure that is given by carousel. And anyway, in the paper of Fernandez, you have very nice Lipschitz interpretation, actually metric interpretation of what is the carousel. Okay? So this is the theorem of Feynman Fernandez. But Neumann-Pichon, they had another thing. They just explicitly constructed the ambient equivalence, not only the outer equivalence. And so, okay, let me just go a little bit to from the inner geometry to the outer. And then the first point, and the first interesting theorem that really somehow is still useful, is the pancake decomposition of Chirta-Kurdyka. So that Kreb decomposition, if you want to go to the French way, that if you have a surface germ, here I just formulate to the surface germ, right? But anyway, you can formulate it for any kind of semi-algebraic or for any kind of dimension, that it means that a surface germ can be decomposed into finitely many ln E, or normally embedded Herder triangles. Okay? And the intersection, sorry? This is outer. That the things who are outer equivalent to the normally embedded Herder triangles. Okay? So that you can subdivide in, you know, that you can have this kind of pictures, right? That really that the inner geometry about this kind of things, right? But still you can subdivide into this kind of pieces, right? Into triangles who are still normally embedded. And then my first guess, okay, we take a canonical decomposition into normally embedded things. And then the point, you can have a minimal decomposition, right? Minimal means that you cannot increase this decomposition. That if you just increase, you have something else that two triangles will be not normally embedded. And then the natural question, is the minimal pancake decomposition canonical? And the answer is unfortunately no. Even here you can see it. But by the way, about pictures, what do I'm drawing? I draw the links, so the intersection with the small spheres. So it's a surface, but it looks as a curve, right? So that, and this means that these things, when they vanish to the singular point, they are quite close. So that even in this simple case, you have two minimal and not equivalent decompositions. And this thing somehow increases a difficulty of their constructing their outer equivalence. Still, let's go. And then, just the first point, probably the most simple thing. Suppose our surface just consists of two normally embedded Hölder triangles, what happens? Does it bring you everything? Perhaps you can speak about a graph of distance function. But look at this example. That before I will describe the tools. Before, when I will go on, I will try to describe this kind of tools. And one of the tools is so-called the Valette link. There is a nice Polish mathematician, Guillaume Valette. And somehow when I do it, I just refer French mathematician Adam Poroshinsky and Polish mathematician Guillaume Valette. Okay, and then here, this Polish mathematician Guillaume Valette just considers a very nice tool that I will be happy to explain. We consider the space of arcs. Arcs means the semi-algebraic arcs, right? And these semi-algebraic arcs parameterized by the distance to the single point. So gamma of t such that the distance from gamma of t to the single point equals to t. So you consider this kind of space of arcs. And here you have the notion of the tangency order. So you consider gamma 1 of t and gamma 2 of t. And then you write what does it mean gamma 1 of t minus gamma 2 of t equals to alpha t to some beta plus O of t to the beta. And this beta is the tangency that we call tort. So the tort of the gamma t is this thing, right? The tangency order. And then the tangency orders define, the v of t is the set of arcs. And then we consider this v of t, and then we take 1 over the tangency order. And then what is funny, that this brings you a non-Archimedean metric on the set of the arcs. And then the theorem of the Valette link, that suppose you have a map which is by Lipschitz with respect to the distance to the origin, to the single point. Then, you what do you have? That this map is outer by Lipschitz, if and only if that this map induced the map to the Valette link is an isometry. So the isometry is this non-Archimedean isometry. Okay? So then this is, I tell that it's Valette link theorem, but it was proved actually before Valette. There were several proofs, and I don't really, there were some Chinese mathematicians that they actually proved it something like, but Valette somehow, he just summarized and he wrote a very nice paper on this link.
Did you say what the non-Archimedean metric is?
Sorry?
Did you say what the non-Archimedean
The non-Archimedean metric is 1 over the tangency order. So you have this tangency order, and you take 1 over Gitter, and then you have the non-Archimedean metric. And this non-Archimedean metric brings you the invariant. Okay?
You have two numbers, right? The 2 arcs, each arc has a number?
For 2 arcs, there is a number.
Oh, what's the number? Oh, the difference.
No, I have this. Yeah, I just take a difference of, and then I take the exponent. Okay? And then another thing that actually when we studied the Valette link, we defined their zooms. It's a sort of topology, because if you take the Valette link with the non-Archimedean metric, it will be totally discontinuous. But still, we define something like connectedness. So we define the zooms. So that, what is a zone? take a sort of set, right? A set of arcs. It's difficult to draw the valid link, but you say that if two arcs who live there, then any arc bounded by them also lives there. So zone is a sort of it is sort of analog of being connectedness. And then you have some function. Suppose you have some function that defines in the Hilbert triangle. Then what do we have? That we want to see the, let's say, we define what does it mean that you have all the exponents of this function on the zone. And then the set of the exponent is a closed interval. Is a closed interval on the set of the set of all exponents. Actually, the set of the valuations on the corresponding minimal structure. Or in this case, we just take the valuations in the set of the terms of semi-algebraic functions. And then I say that T is elementary with respect to F. So you have a function defined there, right? If this ZQ, so the zone of the gamma, containing a gamma who had the same order in this T, is a zone. And then what is interesting for that if you have this kind of normal pair, if you have a normal pair, that actually it means that you draw like this, right? That and it means a normal pair that there is some technical addition that you have two triangles, and then you suppose that the distance here to here and the distance from here to here are always realized in the boundary arcs. Okay? And then we prove the following thing, that if you have the normal pair in this sense, then the normal pair is by Lipschitz equivalent to a triangle and to a graph, to a pair of a Hilbert triangle and a graph of a Lipschitz function defined there. But it's very elementary thing, and now I will show what happens, what can happen. If we don't have this kind of property, this elementary property, but the triangles are still normally embedded, then you can have this kind of pictures. And then you can have plenty of this kind of minimal and maximal, such that the pairs are not equivalent to that. Okay? This is an example, but I don't want to define actually what we did for this kind of normal pairs. Actually, we have a by Lipschitz classification of normal pairs, outer by Lipschitz classification, but it's somehow technical, and when you see this kind of picture, you can see how complicated it could be. Okay, so this was about the outer geometry, and the outer geometry is somehow still in progress. That actually what we did, we just completed the story about pairs of the normally embedded triangles. What about ambient geometry? First, the theorem that if you have two semi-algebraic sets of dimension k who live somehow in the ambient, in the big set, in the who have somehow small codimension, then the outer equivalence implies the ambient equivalence. Okay?
Are you assuming that they are non-degenerate or something like that?
I assume nothing. That outer equivalence, that if the codimension is sufficiently high, so this kind of unique embedding, and this is some kind of philosophy that if the codimension, the same happens in topology. If codimension is sufficiently high, then there are no nodes. There's nothing like nodes. And the same, there are nothing like metric nodes. But what happened with them, the point is, okay, that what happens in R to the 3, it's relatively new already, that suppose you have a surface who is somehow is Lipschitz normally embedded and has isolated singularities. That this is not isolated, by the way. This is isolated. Then anything, whatever it's embedded, whatever it looks like, in R to the 3, then if you have outer equivalence, then you have ambient equivalence. So in R to the 3, outer equivalence implies ambient equivalence. Yes? Just a moment. If you have, it's a good question actually. It's a good question. This we don't know if there is an isolation. I guess we do, but in this paper we didn't prove that. We just proved that outer implies ambient. And if it is not normally embedded, then there are plenty examples I will show you a little bit later. That another interesting tool is that I told you that Valette link is one of the two. And another is the tangent cone theorem proved by Edson Sampaio, saying that what is the tangent cone? We can define the tangent cone not only for the complex algebraic sets, we can define for a definable set in this way, right? And the theorem is that if you have two outer Lipschitz equivalent germs of semi-algebraic sets, then their tangent cones are also outer equivalents. In other, so the tangent cone is outer and ambient by Lipschitz invariant. The topology, in particular the topology. And that is why we can construct then the problem, does outer Lipschitz equivalence implies ambient Lipschitz equivalence in the case that we have no topological abstractions. So that if you have topological abstraction, you take two different nodes, right, and then you have the cones over the nodes, and right, they are outer equivalent but not ambient equivalent. So that this is a topological abstraction. But suppose we don't have topological abstraction. What happens? And then there are several examples. There are examples in R to the 3. So here there are subsets. And if you have these red things, then these red things means they're tangent cones. So that if you have tangent cones who are by Lipschitz equivalent, right, then in particular they have to be topologically equivalent. So here is the example in R to the 3. Here is another example in R to the 4. That there are not normally embedded sets, And you see that there is a link which is a connected sum of 2 or 3 foil nodes. And then you have the connected sum of 2 or 3 foil nodes plus nothing. And these two guys are outer by Lipschitz equivalent and ambient topologically equivalent. But no, they are not ambient by Lipschitz equivalent. And then let me just skip this. And then there is another thing. So how rich this universality theorem, just somehow how rich could be the ambient Lipschitz geometry in the trivial case, if there is no topology. So that the universality theorem proved together with Misha Brandenburgsky and Andrei Gabrielov, that for any node we can construct this kind of surface, xk, such that the length of xk is a trivial node. So all of the xk's are ambient topologically equivalent. And all of them are outer by Lipschitz equivalent. But they are ambient by Lipschitz equivalent if and only if, only if, not if and only if. If I say 5 minutes, right? Thank you. Then, so only if the nodes are isotopic. And this is an example. This is how we can make this construction. And let me come back here a little bit further, because I want to consider another thing, that the theorem, so this is what we say here, this theorem in Archer 3, it's the uniqueness of ambient geometry, a theorem that we proved with David Medeiros. So that if you have this kind in Archer 3, when you have this kind of topological equivalence, and then we have topological equivalence and outer equivalence, then we have ambient equivalence. But this theorem on the uniqueness of the ambient geometry is not true in the case of non-isolated singularity. So here is an example. You can see these are two links, right? But suppose that the exponents, that they are vanishing with the order 2. So these things are not ambient by Lipschitz equivalent. But this phenomena for isolated singularity doesn't happen, for non-isolated, doesn't happen in Archer 4. And we were absolutely sure that this kind of normal embedding uniqueness we have for the we have also in Archer 4. Unfortunately, this is also wrong. This is a recent theorem that looks like proved with Maciej Dinkowski, Edson Sampaio, and David, that for any node k there is a normally embedded surface such that all of them are outer and topologically equivalent, whatever. They are topologically equivalent, but normally embedded. And then they are ambient by Lipschitz equivalent only if the nodes are isotopic. So even in the case of there is the idea how we do that. We just take a triangle. It's, you know, that it's the basic thing of the nodes. That the nodes, let's say, in this for the CMNs, the nodes live just inside. They don't close the node. It's how the CMN make the nodes. CMN or another kind of things, like any kind of shirt that it's a node. But this is this kind of thing that they are not by Lipschitz equivalent. So this is this kind of phenomena that we call micronode. So that here is another picture from the northeast of Brazil, so that everybody are invited.
Okay. So thank you very much. Thank you. So is there any question? No? Then if there is no question, then we...
Okay. So that we take a note.
The variety is an R4.
The variety is this kind of thing. We take a note, right? And then we just glue
In
here.
S3.
Sorry?
In S3?
No, it is in S3. So that leaves in R to the 4. Then we take the fortification of this node. And then we glue to it two triangles who are somehow quite fat.
That's not a real algebraic variety.
But it's a semi-algebraic set.
Yeah, it's not a real algebraic.
Not a real algebraic variety. If you want, we are about to prove that we have a real algebraic variety and the singularity is isolated, then the uniqueness is still going on, but I cannot say that because we didn't write down yet the proof.
And then you put, wait, I'm still asking. The little dot is where?
It's over here.
So is that picture there? That's
Yeah, it's the same picture.
that picture.
Because we make this kind of...
Okay.
Can you change semi-algebraic by semi-analytic?
Yes. We can everything, yeah. That any kind of polynomially bounded or minimal structure. Yeah.
Okay, so there is no more question. We thank again the speaker and the rest of the speaker of the session.
Again, congratulations.
Okay, and now for the lunch, the lunch is in the building in the back, in the last floor. So we are going to follow the people, local people.
Sí, hace rato también. Andaba así, mejor me salí. Ah, sí.
Muchas gracias.
¿Qué pasó, Carmen? ¿Ya está cerrando, Fernando?
No voy a cerrar.
Thank you.